Hi everyone, welcome to the class. Welcome to Vedantu JEE English. I'm Diksha Kaushal, your chemistry master teacher. So everybody do let me know in the chat box if I am clearly visible and audible to all of you or not, so that we can start with the lecture 1 of JEE Booster series, where firstly we are going to pick up top very important chapters, right? And I'm going to start with GOC, right? Now ma'am, why have you started with GOC? I'll tell you the answer behind that. Because full organic chemistry, the base is general organic chemistry. If you're not good in GOC, then like the questions that they will ask you from the reaction part also, you will find it tough, right? Second thing is, in GOC, directly from electron displacement effect like inductive, resonance, aromaticity, they directly ask you the questions, right, based on stability, acidity, basicity, right? And all of this, right, is so important that you will see I have picked only the latest year questions, like latest PYQs I have picked. I have not picked PYQs from 2019 even. I have picked mostly, you will see 2024, 2025 only, and you will see how many same category of questions are being repeated, right? Maybe the way they ask you the questions may be different, but category is same, that the flow of the lecture is going to be based on those questions. And I promise you one thing, that in the end of this lecture, you will be able to do all the questions related to GOC. That's my promise to you, right? All you have to do is be here, be attentive in the class, right? Don't be someone like who is there in the class just for the sake of being in the class. I'm in the class, but I'm not attentive. That will not work when we talk about GOC, right? You have to be fully attentive, right? And if you ask me, do I need to make notes here, right? You will get the PDF of these notes, so don't worry about that. You will get the PDF. You can just go through the PDF and you can make your notes afterwards also. But one thing, you should always have one pen and one notebook so that you can write down yourself, not for the notes but just for answering things out, right? Because this is not a theory thing, right? GOC you have to understand. It's not a cramming based thing. You have to understand GOC, then you have to apply GOC. It's a totally conceptual thing. You have to understand the core concept here, right? In organic chemistry, still you should, okay, you can remember things, okay, this is the mechanism, this is the reaction. Obviously there is logic behind that, but in this case it's like you have some concept, then based on those rules you will apply those concepts. So the good part is no cramming is needed, right? But the bad part for those students who love cramming is that you have to understand things, right? So everybody ready for this lecture, everyone? Anirudhin, Kach, Nandini, Lovely Kana, Santosh, Radhika, Chandu, hi. Yes, everybody, do let me know concept you're going to cover in this session. Okay, so I'll tell you what are the concepts that I'm going to cover in this particular lecture. So guys, if you see what are the topics that I'm going to cover, these all topics I'm going to cover, right? So first is basics of organic chemistry. We'll understand a little bit basic of organic chemistry that is needed to understand this particular lecture. Then we will understand electron displacement effects, like most important electron displacement effects that are in your syllabus is inductive effect. Then you have resonance. We'll see the detail of resonance and mesomeric effect. Then we'll see what is the difference in resonance and mesomeric. We'll see hyperconjugation. Next concept is aromaticity. Then we'll talk about annulenes also. Like in aromaticity, we'll talk about annulenes also. Then stability of intermediates based on Barhi. Now ma'am, what is this Barhi? Barhi, you won't see this term in books. This is how I ask my students to remember this thing. B for back bonding, aromaticity, resonance, hyperconjugation, inductive. So stability of intermediate is exactly why it is so important, because it is tough to understand. If you know all these concepts individually, then you also have to know how, this is a question. Now in this question, should I apply resonance? Should I apply aromaticity? Should I apply inductive? when all of them are applying, which will be given the priority, right? All these things we'll study in stability of intermediates. Then we will study acidic and basic strength, which is based on stability of intermediates only. Then last one is ortho effect in acidity and basicity. So this is going to be the overall lecture for today, right? Okay. Ready everyone? Yes. Definitely Chinu, you can definitely understand these concepts as well, because that is in your syllabus also, right? Okay, so now let's see this one. First is the basis of organic chemistry, the basic. Basic is that organic chemistry is all about these things. What are these things? There is a reactant, right? And there is a reagent, right? Reagent can be like you have H2PD, you have hydrazine, you have so many reagents, like you have PDBSO4, that is Lindlar's catalyst, that is used in Rosenman reduction, right? You have different, like you have sodium and dry ether, which is used in Wood's reaction. So all these are reagents, right? So you have reagent, you have reactant, right? And to make these two things react, in some cases you use solvent also. Then after this, what exactly happens? They go through either they will go through a transition state, or they will make a intermediate, right? Okay, once reactant and reagent will react, they will make either transition state or intermediate, that we will see in the reaction part, this particular thing. And after that you will have the product plus the byproduct, the major product plus the minor product, right? And in GOC, what exactly we focus on is not, wait a minute, okay. So in GOC, we focus on these things, right? Not exactly, not even this, we focus on this particular part of organic chemistry, right? That is actually telling us GOC, that is majorly focusing on the intermediates. That's why we have to learn all these effects to tell the stability of the intermediate, which intermediate is stable, right? So if you talk about intermediates, there can be different types of intermediates. So majorly that we discuss in GOC is carbocation, then there is carbanion, and then there is free radical. If on the carbon you have an orbital that is vacant, that has no electron, that is carbocation. When it has one electron, that is free radical. When it has two electrons, that is called as carbanion. And we are going to discuss about all of these intermediates and their stabilities in the upcoming session. In this session only. Yes. So let's understand what is electronegativity. Before going towards these electron displacement effect, let's understand what is electronegativity. Right now, if you have a pair of electron, this is A and this is B, right? And let's say fluorine is I am saying, let's say B is more electronegative, like fluorine. Like for example, you have H and F, right? We know that in H and F, H is less electronegative, fluorine is more electronegative. So that's why shared pair of electron will be towards fluorine. So if I say this is electronegative more and this is less electronegative, in that case the shared pair of electron will be, it's not like it has totally moved to B. It means that in the same bond, it is slightly inclined towards B. It is not moving, it has not shifted, right? It has just displaced a little bit. That is called as electronegativity. And electron density is electron cloud surrounding an atom, varies with charge. Now, how much electron cloud is there? Like you have A negative, A2 negative, right? A negative will have less electron cloud because there is only one negative charge. A2 negative will have more electron cloud because it has more negative charge. Okay, so electron cloud is dependent upon the charge, right? If let's say we talk about this thing, right? Now in this case, electron cloud is maximum in case of M3 negative because minus charge is very high, and here plus charge is high, that's why electron cloud is decreasing here, right? So that is the order of electronegativity or the order of electron cloud, okay? Now why I am teaching you all these things? In the end, the major thing that we are going to discuss is about carbocation. So I'll just draw this here, carbocation, right? Now tell me about carbon, everyone, right? Tell me about carbon. Yes, tendency to attract, shared pair, very good, Thilai, very good tendency. And Nandini, yes, okay. Okay, hi Sameer. Yes, okay. So let's see. Let's see this thing, basics of organic chemistry. Guys, let's see this thing. In this case, if you talk about a carbon, right, what is the atomic number of carbon? See, this much, if you can relate in organic chemistry with organic chemistry, we'll learn a lot of things, right? So if you see carbon, that is atomic number 6. Right, so it is 1s2, 2s2, 2p2, right? This is the electronic configuration. So outermost orbital, actually it hybridizes to form 4 orbitals, right? That is, it forms 4 orbitals, that is, and it fills 4 electrons here, like this. So in C positive, what you have, right? In this case, what you have in C positive, okay, this is for carbon, I am just writing it down, wait a minute. So I am just making a box here, right, I am filling the electrons, this is in case of simple carbon, right, in case of carbon, this is 1, 2, 3, 4, okay. So what exactly is there? In case of carbon positive, carbon negative and carbon free radical, what you have a p orbital, right, which is unhybridized. I am not talking about hybridized p orbital, I am talking about unhybridized p orbital. So that means in this case, hybridization will not be sp3. In case of C positive, right, what exactly will happen? This will have 3 hydrogens or any bond already attached to it, and this will be positive. That means out of this, carbon has lost 1 electron, right? Now it has sp2, it is 1, 2, 3 electron, and 1 p orbital is unhybridized. That means 1s and 2p orbitals. See exactly what is the case with carbon, okay? So I'll just write it here, I'll just draw it here. So what is the case with carbon? If you see this here, with carbon, guys, you have 1, 2s and 3 2p orbitals, right? So what exactly happens in case of carbocation? In case of carbocation, the hybridization is only sp2, right? This orbital remains unhybridized and you take out 1 electron from here, right? So basically earlier we know that what should have happened, this should have 4 electrons, but in case of carbon positive, what you have is you only have sp2 hybridized orbital where 1 electron is filled, and 1 p orbital is unhybridized, which is totally empty. That is called as a carbocation. That's why it is sp2 hybridized, okay? Here carbon is sp2 hybridized, right? In case of free radical, what you have? In case of free radical, what you have? You have this situation where 3 bonds are there. There is this electron, right? It's not empty. This p orbital has 1 electron in it. So here what has happened? Here also what has happened? This particular carbon, right, in the form of free radical, it has 3 orbitals, right? And this is a p orbital. It has 3 electrons here, 1 electron here, right? But this one particular electron is making free radical here. That means this one particular electron is making free radical here. That is your free radical carbon, right? Then when you talk about carbanion, here in this case you have 2 electrons. That means in this orbit, in this orbital, here you have sp, this one, wait a minute, yes, okay. So here it has gained one more electron here. So what exactly has happened? This is p orbital and here it has gained one more electron. That means here you had 3 electrons already here. This is 1, 2, 3 and one more electron it has gained. That is why this is becoming a negative charge here. So that's why this is a carbon ion. So carbocation is empty, free radical is 1 electron, carbon ion is 2 electron. Okay everybody? Tell me everyone in the chat box if that is clear. Now a very basic thing about this, that is the difference in lone pair and free radical. Who will tell me? Ma'am, but see, carbocation is empty, free radical, empty orbital, free radical is 1 electron, carbon ion is 2 electron and ma'am lone pair is also 2 electron. No, yes. Anyone of you who can tell me what is the difference? Yes. What is the difference in carbon ion and lone pair? What is the difference in if I say there is an atom that has negative charge and there is an atom which has lone pair? Right? What is the difference? Let's see who will tell me that, because these are the basics that you must know to understand organic chemistry. Right? Otherwise, you will always get stuck in mechanisms. You won't be able to understand because this basic thing is not clear, right? Okay, so everybody tell me if there is a negative charge, right, on an atom, right, or there is a lone pair, both of them has 2 electrons. What is the difference? I am waiting for your answers here. This is, let's say, A and this is B. Okay, let's say yes, this is A and this is B. Okay, now this is a covalent bond, right? This is a covalent bond. Let's imagine, no, it's not reactivity, it's not carbon ion, no, that's not, no, Sameer, we can't say that carbon ion it's a charge, but why we are taking it as a charge, right? Both of them are showing 2 electrons. Lone pair means 2 electrons, carbon ion means 2 electrons. Then what is the difference in that part? Yes? Yes, you are slightly there. Sameer, you are there, but still there is one major difference, right? That major difference is, if you talk about A and B, let's imagine B is more electronegative. So I'll take it as partially negative. This is partially positive. Right, so lone pair, these shared pair of electrons will be here, right? So now let's see that this bond breaks, okay? This bond somehow reacting with some reagent or something, I break this bond, right? Now this will be A positive and this will be B negative. Why so it will be B negative? Because here in this negative part, if you talk about the electrons here, right? Here 1 electron is of this A and the other electron is of this B, right? So negative means it has actually acquired that electron from the atom with which it was making a bond, right? So simple thing is, it's like you and your friend, right? You are eating pizza, you have ordered pizza, right? So a small pizza you have ordered which has only 4 slices, right? Because considering how much you will eat, right? So you have ordered pizza, 4 slices are there. Now you were supposed to share it because let's say that pizza is of 120 rupees, right? It's a ready wala pizza. It's like a local street pizza. It's not a hi-fi pizza, okay? So 120 rupees it is, right? Now you have given 60 rupees, your friend has given 60 rupees like these. 1 electron. Now your friend is very clever. He was like, I'm too hungry, please give me full pizza and all that. You eat something else, right? And you got so emotional, you gave him full pizza, right? Now that is this situation, right? Even though they both were giving the electrons here, even then only B is having those 2 electrons. So when we say negative charge, we actually want to say the electrons that you have here, one electron is of B and one electron it has taken from someone else, that is the difference, okay. But in case of a lone pair, let's say there is B lone pair, that means both the electrons are of B, right? Let's say there is a B and there is lone pair here, that means both the electrons are from the electronic configuration are from the B only. Like if I say lone pair on oxygen, you have these lone pair means that these are the electrons of oxygen only. They have not gained it from somewhere, they have not taken it from somewhere, the electrons belong to that B only. That is a major difference of negative and lone pair, right? This will help you to understand resonance here, right? Because in resonance students do mistake, right? They convert negative, they convert bond pair to lone pair sometimes, right? So this is how you'll be able to understand that how to do this, right? Okay, great. Right, everybody? Yes. Yes, Sameer, you can just subscribe to the channel Vedantu JEE English and you will get to know about my class. And like tomorrow, I'll tell you the schedule of next week also. Tomorrow I have class of electrochemistry at 5 p.m. right? Okay, and tomorrow I'll tell you the schedule, proper schedule of next week, right? So it's not daily. In 1 week I have 3 classes. So it's on Tuesday also I have, right? Rest of things I'll tell you, I don't remember it clearly, right? So I'll tell you that in tomorrow's lecture. But yes, all the classes next week for like chemistry classes will be at 8:30, so you can join that, right? Even after your classes, right? Because as far as I know, you are in Vedantu learning centers, so I think you will be busy before that, right? So after that you can easily join, right? Okay, everybody. So let's see next thing, right? So we have done it. Now let's understand electron displacement effect, right? Now we know that electron is being displaced, right? Okay, can you please teach this part again? Okay, sure, Stuti. See Stuti, one simple thing is that when I say B negative and when I say B lone pair, what is the difference in that? Difference is when there is B negative, that means these 2 electrons that it is carrying, one electron is of its own, it belongs to B only, right? One electron it has actually gained from some other atom, that is B negative. If both the electrons are from different atoms, that is B negative. If these lone pairs, if I am considering 2 electrons as lone pair, that means these 2 electrons that I have here belongs to that atom only, it has not gained it from somewhere else. Okay, right, everybody? Understood? No, carbon ion is not sp2, right? This is not sp2. Wait a minute, this is not sp2. Yes, this is not sp2. Carbon ion is that only. Carbon ion is, I'll tell you about that also. Carbon ion in delocalization is not is sp2, but in non-delocalization it is sp3 only. Okay? In now as of now we are talking about non-delocalized, but when I'll talk about delocalized in the resonance, then I'll change this concept. Not change, I'll elaborate this concept for you, right? As of now I'm just talking about simple carbon ion. So yes, electrons will be this and here it has gained 1 electron, right? So you can definitely say that here, right, this is sp2 only, sp3, because you know if you see this here, it will have 3 sigma and 1 negative, so it will be sp3, right? This will be sp2, right? Okay, yes. Now let's talk about this one, that is electron displacement effects. Let's see electron displacement effect. Yes, everybody, right? Right, so let's see, now we have electron displacement effect. One is permanent effect, other is temporary effect, right? So firstly, we are going to talk about permanent effects. Permanent effect means, wait a minute. No, this is actually opposite. Yes, okay. So permanent effect means it is not influenced by the outside reagent, right? For example, if I talk about inductive, mesomeric, hyperconjugation, they don't depend upon the external reagent. It's not like these effects will only take place at a certain conditions. They will take place if that compound is there, this effect will be there. It's not like if they are reacting with hydrogen, they will behave in a different way. They are reacting with Cn negative, then this effect will happen or not. They do not depend upon the external reagent. They only depend upon the reactant. That is why they are called as permanent effect. That means these effects are not dependent upon reagents. Then there is temporary effect. Temporary effect is the effects that are depending upon the reagents, right? So that is electromeric effect that we are going to discuss in today's class. Okay, so let's understand one by one. I am going to start with inductive effect. So guys, everybody, let's start with inductive effect, everyone. Let's start with that. Let's start with inductive effect, right? Okay. Before this, before inductive effect, always remember, we'll also talk about the priority order of these effects. If you see, out of mesomeric and resonance is same only. I'll tell you the difference, I'll do it in detail, right? If you talk about the dominating nature of these effects, usually mesomeric is prioritized, then hyperconjugation, then inductive. Usually this is the priority, right? But in case of halogen, things are very different. In case of halogens, you have inductive first, then you have mesomeric, then you have hyperconjugation, right? Okay, so we'll talk about this, why it is so, right? Why these things are so, but for that you need to understand each of these effects in detail. So let's understand these effects in detail. Okay, only then you'll be able to understand this particular part, right? Okay, first is inductive effect. So guys, let's talk about, now the class has actually started, right? So inductive effect, this effect is actually based on the electronegativity, right? So if you talk about A and B, they have a sigma bond, right? One will be more electronegative, and the one which is more electronegative, the electrons, the shared pair of electrons will be towards that particular element, right? And that's why the electrons has displaced, and that is why we are saying that actually inductive effect is dependent, is actually displacement of sigma electrons. Pi electrons we are not talking about. We are only talking about sigma electrons. We are not talking about delocalization. We are talking about displacement here. Displacement, not delocalization. Okay? Not delocalization. Right? So let's see. It is distance dependent. Right? It depends upon the distance as well. Right? And it develops in the partial charge. Okay? It results in the development of the partial charge. So exactly what happens? Let me explain you the first point here. It operates only on the sigma bond. That means only sigma bonds. It will not operate on the pi bond, right? Then the third point results in development of partial charge. Ma'am, what do you mean by that? That means this is A, this is B, because here shared pair of electron is towards B. So this is partially negative, this is partially positive, right? So that thing will be there, right? Okay. Then there is distance dependent. That means effect is negligent after third carbon, right? Now, let me explain you that with the help of an example. Let's say you have this C, this C, this C, right? And this is OH here, right? OH is partially, this is electronegative, so that is why it will behave as a effect that is taking out the electrons towards this side. This will be partially negative, this will be partially positive. right? Partial positive charge will be maximum on this carbon, then less on this carbon, then even less on this carbon. That means with the distance, it is going to decrease. The inductive effect is going to decrease. That means the effect after third carbon, the effects, that means the you cannot see this effect after third carbon, right? After third carbon, this effect will be negligible, right? This effect will not exist after third carbon. It will become so small, right? Okay. Yes, everyone. Now let's see this thing, that there are two kinds of effects that you have in inductive effect. First is plus I, then there is minus I. Plus I effect simply means that in this effect, right, it is shown by electron donating groups. That means you have electron donating group, they are going to donate the electron to this side. If earlier the shared pair of electrons were here, now with respect to, and we are always comparing this with the hydrogen, the standard here is hydrogen. If carbon with hydrogen, the shared pair of electrons are over here, then they are over here. When you talk about, when you have any electron display, any electron donating group, that means this delta X that you can see, this is defining the displacement of electron that has occurred. Similarly, in case of electron withdrawing groups, right, that means, like, let's say in place of hydrogen, when you have hydrogen here, the electrons are over here. These are the two electrons, right? Now you have electron withdrawing group. That means the one which is withdrawing the electrons, it is going to take the electrons to this side, right? That means the electron has displaced from the original position by this much x, that is this much distance, that is called as displacement of electrons, right? So plus I and minus I, plus I is shown by electron donating groups, minus I is shown by electron withdrawing groups, okay? Usually you will see in case of plus I, what are the groups that you will have here? Firstly, in the case of plus I, that is donating, you will have those molecules which will have negative charge. That means the one which are electron rich, which has electrons, right? Second is alkyl groups, right? You have CH, you have CC, you have CD, you have CT, all these will show plus I effect. Let's talk about which will show how much plus I effect, right? Everybody, let me know in the chat box if till now you have any problem. Tell me, if till now, if you have any problem, do let me know in the chat box, right? Now, in the case of plus I effect, let's talk about it, everybody. Let's talk about plus I effect. Yes, students, yes. Everybody in the chat box, let's talk about plus I effect here, and yes, very good. So I hope so you are liking this session, right? If you like enjoying this session, then do hit the like button there, right? That motivates me a lot to do more for you, right? Okay, so that is our motivational thing. When you like the session, when you comment down, right, about what you feel about the session, right, that pushes us to do more for you, right? So let's see this plus I effect, that is shown by negative charge species and it is shown by alkyl groups. Let's see that. First is negative charge, that is CH2 negative, NH2O negative, CO negative. Now, ma'am, why this is the order, right? Ma'am, why this is the order here? Let's see that why this is the order. The simple reason for this order is that here electron negativity of oxygen is maximum, then nitrogen, then carbon. That means this will have least electron donation because it is very clever. Its electron negativity is so high that it does not want to give the electron. It does not want to donate the electron, right? And that is the reason you have CH2, then you have NH2, then you have O negative. Now, this is also O negative, ma'am. This is also O negative. Then, ma'am, why this has more donation? Because here only on one oxygen you have negative. But here you will see from the resonance, I'll teach you this in resonance, that how because of resonance electron will get displaced. See how this is interrelated with each other, right? So that is the reason that here this negative charge is actually distributed among two oxygens. That is why it has less plus I effect. Donation is less. Then in case of 3 more the alkyl groups, more is the plus I, right? It has 3 alkyl groups here. It has only 2 alkyl groups here. It has only 1 alkyl group, and that's it. And this is what you have here, right? Wait a minute, and this is C, this is supposed to be CH3, right? And always remember that tritium has more plus I effect as compared to deuterium, as compared to simple hydrogen, right? As compared to hydrogen. So these are the 3 isotopes of hydrogens, right? T, D, H, right everybody? Yes, Samir, I'll definitely do that. Don't worry about that. I'll definitely do that, right? Okay. So we are going to do this only, right? Then minus I effect, okay. In case of minus I effect, what you have? Electron withdrawing. That means this is going to be electron deficient. So it is going to withdraw the electron. It is going to take the electron, right? So it should be electron deficient. It should be positive charge, or it can be having partial positive charge. Let's say there is A and this is B, but this is partial positive because this is a less electronegative. So we can definitely say less electronegative, right? Okay. Sorry, more electron. Why I am saying less electronegative? Withdrawing, no? Yes. Withdrawing means more electronegative it should be, right? For example, you have X halogens, then you have oxygen, nitrogen, carbon. Now this will have more minus I than less because they have more electron, they are more electronegative. That is why their minus I effect is going to be more, right? Then guys, next is, this is the series of minus I effect that you should remember as it is, because as it is also this is asked, okay? Right? Okay? Right? Yes. Kritik, that is not a part of GOC, so I won't be teaching you this here, right? Okay? Yes. Tell me one thing, this is minus I effect, right? So if you see NF3, NR3, SR2, NH3, NO2, SO3H, CN, CHO, COH, fluorine, chlorine, bromine, iodine, OR, OH, C triple bond, NH2, benzene, ene and H. Out of this, the most important ones are, you should know OR is more than OH. Then you should know that here you have this thing. That means you have NF3, then you have NR3. Why NF3 has maximum? It has 3 fluorines. Fluorine is very electronegative in nature. Highest electronegativity 4. It has electronegativity 4, which is highest. So that's why minus I effect is maximum. But the important part is why NR3 is greater than NH3. Why, ma'am? Why it is so? See. If you see this thing here, this is NR3, this is NH3. If I see the logic of plus I effect, right? So more the alkyl group means this will have plus I, this will have plus I, this will have plus I. So they will donate the electron to this one, right? So this nitrogen already has so many electrons by the donation of this R, that it doesn't need to take out electron from someone else. So it should be like this, isn't it? By the logic of plus I, it should be like this. But why that exception is there in the series, right? Okay, why that exception is there in this particular series? Tell me, why this exception is there? Ma'am, can you please tell us the trick? I remember this from, like, not from a trick, like as it is, right? But if you're asking about a trick, then what I'll do, right? I'll make the trick firstly, because some of you, you know, the problem is that when I make a trick, I don't know if you will relate to that trick or not, right? So I prefer not giving the tricks to the students, but I have seen in past few weeks students are asking me the tricks on learning DNF block, ma'am, P block, ma'am, orders, ma'am, spectrochemical series, ma'am, and now this one also. So what I'll do, I'll surely make, now I'll start making the tricks. So tomorrow also I'll give you a trick on those things, right? Okay, so don't worry, I'll make a trick on this. I'll see easy one if I can make. In English I'll make, because this is an English channel, so I'll make a trick in English. But making a trick in English is a tough task, right? In Hindi or any regional language it's quite easy, but I'll try my best, right? Okay. So now you see this, it should be the case, but now exactly what happens? These groups are very bulky. So because of their bulkiness, what exactly happens? Their bond angle increases, because bond angle and electronegativity is directly proportional, so electronegativity also increases. That is why more the electronegativity, more is the minus side effect. So that is why this is a very important thing, that NR3 is greater than NH3. Okay, this one is very, very important, right? Before doing this question, I want to tell you something about acidity, right? Only then we'll proceed. Yes, that is steric hindrance. Very good. Effect are same, or there is any subtle difference? Yes, Rishi, there is a difference. There is a subtle difference. Yeah, the word is exactly right. There is a subtle difference here that we will talk about when we'll study resonance. After this only we'll start with resonance, right? So firstly, let's understand inductive effect. If you talk about let's say acidity, okay, firstly to answer this question you should know acidity as well, right? When I talk about acidity, guys, right, you must remember, if I talk about an acid, right, acid means the one which is giving the electron, right? Acid means the one which is giving the electron, right? Acid means the one which is giving the H positive, right? So if I talk about an acid, that is Ha, it is giving H positive. How easily it gives H positive will define how much good this acid is. If you have to tell the order of acidity, you should know which has ease of giving H positive. Ease of H positive will be given by how much stable is the carbon ion that you have, right? See guys, this is from our simple life. Tell me one thing. If I tell you after studying you will not get anything in life, you will be very poor, you will not get any job, right? You will be jobless. After getting into IITs, you will be jobless, right? You will not have good financial stability. Will you still would want to learn all these things that you learned? No, you are like, I'm not mad, ma'am. Why would I study all of this if you tell me I'm going to get nothing after this, right? See, no matter how much motivation and all I give you, how much you love some subject, you are studying only because of one thing, right? That is, you know that if you get into that particular college, you're going to have good placement, you are eventually going to earn good, right? And financial stability is all what we need in the end, right? Isn't it? Because we know that no matter anyone says that money is not important, we know that money is important, right? If it is not important, then why, when you have no money, when you see someone with, you know, no money, why they are crying? Because they cannot afford a good food for their family, because they cannot afford, when some family member is not well, they can't afford a good hospital, right? Isn't it? So money is important. It's not like that. And you know that. You are here because you know that. You are very well wise. You know this. And that's why you are like struggling all these, every single day you open the book and you study. Why? Because you want to be there. You want to help your family financially, isn't it? Right? You want to have that reputation in the society. Right? So you want to be stable. That's why you are giving up on everything. So if I tell this acid, If I tell this acid, you give upon proton, you give me proton, and you are going to be very unstable. Then this acid will be like, I am not psycho. I'll not give up this proton. That means it will behave as a bad acid, right? If I say you will be a very stable carbon ion, then this will be like, okay, I'll give up proton, and now it will be in a stable. That means a very good acid, right? That means for a good acid, all you have to focus is the stability of carbon ion. And always remember one thing, keep this in your mind, one thing, that is, if you have a carbon ion or a carbocation, right, the difference is, simple way of remembering, take carbocation as money and take this carbon ion as stress. Okay? Oh my God, I have a lot of money, right? And someone is giving you more money, right? Let's say someone is giving you money. Will you become happy or sad, right? If I start paying you, that you have to study, I'll start paying you for you studying, I'll start paying you. You'll become so happy. If I take out money, if you're already electron deficient, you already don't have money, and someone is taking that money from you, you will be unstable. So when you give someone money, they will be happy. When you take out money from someone, they will be unhappy. That means when you have electron donating groups, carbocation is stable. When you have electron withdrawing group, carbocation is unstable. But the case in case of carbon ion is different. When you have electron donating, if you already have stress, someone is giving you more and more and more and more stress, you'll be like, please get out of my life, I don't want you, right? You will become very unstable, right? So if someone, you're already under stress, someone is giving you more stress, you will be very, very unstable, you will be very unhappy, right? And you are already like in so much stress, you're calling your best friend, hey, this and that happened, I hate this person, this and that, you're just cribbing about this and that, you're venting out, right? And you're suddenly, after that talk, you're like, oh my God, I'm so relaxed. What exactly? And you love your best friend, isn't it? Why? Because they make you stable. They make your mental health stable, right? So when someone is taking stress out from you, you will become very happy. You will become very stable. You will become happy, right? So that means if I'm talking about the stability of a carbon ion, all I'm looking for is the electron withdrawing group. More the electron withdrawing group, more the power of electron withdrawing effect, more the power of minus I, better will be the carbon ion, stable it will be. Stable carbon ion means good acid, right? So if you talk about this thing that they have asked in JEE 2024, a very, very stable question, right? Okay, Sameer, I would love to teach, right? But I would love to teach in Hindi, English also. But this channel is Vedantu JEE English, and this channel is to create no barrier, right? Because of the language, right? So English, we all know that all over India, every single student can understand English, and I am not literally not speaking that much hi-fi English, right? My English is very local, right? Local English I am speaking, right? Why? Because I know local English only, right? I don't know hi-fi English either, right? But still, why I'm saying this? Because we don't want to flaunt that, hey, I know these vocab words, I have this accent, no, we are not here for all of that. Why we are teaching in English? Simple thing, because we know that there are students out there who don't understand Hindi, and in their regional language, they don't get really good content, right? And that's why they struggle a lot, right? In Hindi, they struggle a lot. That's why we are here teaching in English, because we know that whether it's Hindi audience or there is audience that don't understand Hindi that much, they are also comfortable in this, right? Okay. So if you see this here in this case, as you can see, this is H, this is CH3, this is CH3, CH2, this is CH3. So if you talk about plus I effect, one thing I'll write for plus I effect here, right? More the number of, right? First thing is, you can say plus I effect is directly proportional to degree of carbon degree of carbon, whether it's 3 degree or 2 degree, it means 3 degree is maximum, then 2 degree, then 1 degree. And if you have all of them as same degree, then it depends upon the number of carbons. More the number of carbons, more will be the plus I effect. That is the reason here what we are going to have, right? Here we are going to simply say that more the number of carbons, more will be the plus I effect. This is more carbons, then 2 carbon, this is 1 carbon. More carbons, more plus I effect. More plus I effect means if you talk about, wait a minute, carbon ion, we are talking about. More plus I effect will make it unstable. Yes. Okay. More plus I effect will make it unstable. So this is more plus I effect, right? We can say this will have 3 carbon has more plus I, then 2 carbon, then 1 carbon. This is the order of plus I effect. If you have donation of electron more on the carbon ion, if I say this is negative, this is negative, this is negative, this is negative, right? This is 1 CH3, this is CH3, CH2, this is CH3, CH2, CH2. So that means maximum plus I effect is here. So making it very unstable because electron donating effect makes it unstable. So answer will be B is the correct answer here. Okay. Yes everyone, let's talk about now resonance, and why I have not taken that many questions of inductive effect here, because guys I want to take you to stability of intermediates. We'll do a lot of questions there, and those questions are actually based on the inductive plus resonance plus aromaticity plus hyperconjugation. So we'll do more questions when we study all the effects, right? Okay. Now let's talk about resonance. Let's talk about resonance, everyone. Let's talk about resonance. Wait a minute. Yes. So, let's see this here. Resonance. When a single Lewis structure cannot explain all the properties of molecule, multiple structure like resonating structures are used, right? For example, resonating structures, or they are also called as canonical form, and they are also hypothetical in nature, right? Resonance hybrid is real structure, delocalization of pi electrons, and conjugated system. So simple is that we talk about benzene, right? In reality, if we talk about benzene, we draw it like this. We also draw it like this. We also draw benzene like this, right? Single bond, here it is double bond, here it is double bond, here it is single bond, right? So alternate double single bond, we also draw it like this, right? We also draw it like this. So what exactly is the correct structure, right? So what we say that these two are the resonance hybrids. These two are the resonance hybrids. Okay? And this is, and this one is resonating, this is not hybrid. These are resonating structures, and this is hybrid. This is resonance hybrid. These are hypothetical structure that we draw, right, to understand the reactions, right? That's why in mechanisms everywhere you will see these structures of resonance, these structure of benzene. But actually we draw, this is a real structure of benzene. And what do you mean by this circle? This circle simply means that exactly what is happening. If we say this is pi bond here, pi bond here, pi bond, and here I am saying this is pi bond, this is pi bond, this is pi bond, right? This is hypothetical, but in reality, what is the real thing? In reality, we say that pi bonds are all over here, right? That means pi bonds are revolving from, they are delocalizing from this point to this point, this to this, this to this. They are just moving here and there. They are shifting here and there. That is called as delocalization of pi electron, right? That there is a system in which pi electrons are moving from one place to another, right? So the real structure of benzene is where pi electrons are all over these carbons, but still we draw single bond, double bond, single bond, double bond. That is a resonance structure, resonating structure that we imagine to make the reaction simple for us. That's why they are saying single Lewis structure cannot explain all properties. Multiple structure are used. That is the reason, which are actually hypothetical. It is purely a theoretical concept, right? Okay, to understand the reactions better, right? Okay. Okay. Yes, Rema, I'll surely try to do that, right? Otherwise, if I don't do it in this theory, in this particular series, I'll do after that, right? Okay, now resonance is, if you see this here, all pi bond, and now what are the conjugated system that shows resonance, right? So conditions are all p pi d pi must be continuous, right? There should be no break in the system. Second is all p pi d pi must be parallel to each other, right? There should be no break means if I talk about double bond, single bond, double bond, single bond, double bond. If I say this is double bond, double bond, then single bond, then double bond. Then this resonance has a break. Okay, only here it will show the resonance, right? So that is why what we are saying, there should be continuous, right? There should be no break in between the pi bonds. Second is they must be parallel to each other. These are the two conditions. Let's see how. What do you mean by parallel, right? Okay, parallel means like these two orbitals, they can only, because in resonance actually the orbitals overlap and that's how they shift the electrons. That is why these two orbitals, because they are parallel, that is how they can shift the electrons from one place to another. These electrons are parallel, that's how they can shift the electrons from one place to another, right? Okay. So one by one we are going to talk about the types of resonance that we have. First type is back bonding, right? Okay. First type is back bonding. So let's see what is back bonding. In case of back bonding, you must have a electron rich species and an electron deficient species, right? Ma'am, what do you mean by that? One should be electron rich, one should be electron deficient. What I mean by that? So if I say this is vacant orbital, this is a fully filled orbital, then this should be parallel to each other. They should be continuously in the continuous form, only then they can give electron to one another, right? Other thing can be like this is a metal which has vacant d orbitals and this is oxygen which has lone pair of electrons. So it can donate the electrons from this place to this place. That is also called as back bonding, right? That is also called as back bonding, p pi, d orbital vacant back bonding, right? So simple thing is that in the case of back bonding, you should have two conditions. One thing is one should be electron rich, other should be electron deficient. Now I am going to give you some examples on this. For example, you have C positive, this is OH, okay? Then you, let's say you have CH2, you have NH2, right? Then let's say you have CH2 and you have BH2, right? So let's say you have these examples here. Let's say you have here, you have CCl3 negative. You should tell me, you should be able to tell me how many of them shows resonance here, right? Okay, tell me. Back bonding is shown in which of the following cases? Tell me. Everybody in the chat box, tell me about it. Yes. Chemical bonding also will do. Don't worry. Yes, it is going to be 3 hours. It's not like totally 3 hours only. I'll try to complete it before that also, if it is possible, right? Yes. Tell me everyone. See, here if you see, this has lone pair of electron, this is electron deficient, this is electron rich. That's how you will have a resonating structure, that is CH2. This is double bond, this is OH, this is positive, right? So lone pair will be shifted here, making a double bond, right? And here it will have a positive charge, because whenever lone pair is shifted to bond pair, then it always carries a positive charge, okay, right? And here it has gained one electron here from these lone pairs, that's why it will become neutral, right? So here also you have lone pairs, this is electron deficient, this is electron rich, this is carbocation, that's why it is electron deficient, this is lone pair, that's why it is electron rich, that's why electrons will shift here, and you will have CH2. Double bond, this is NH2 and this is positive here, okay, right? Next is, if you see, now tell me about this. Will it show any kind of resonance or not? Let me see if you can tell me, if you can tell me this or not. This is first, second, third, this is fourth. Now tell me about this everyone. Will this third one will also show any kind of resonance or not? Any kind of resonance, first and second alone. Sai is saying, ma'am, first and second alone. Okay, and what about third one? Sai Krishna. Now can I crack J? Arey yaar, yes, definitely. Gir Babu, definitely you can do that, right? There is no doubt in that, right? Tell me. CH2 negative BH2, it will show any kind of back bonding or not. Back bonding is a kind of resonance. We need electron rich and electron deficient here, guys. If you see this here, this is definitely electron rich. But is boron electron deficient? Yes. Boron has 3 bonds. That means it has 1, 2, 3, 4, 5, 6 electrons. And for boron to be not electron deficient, it should complete the octet. But here 8 electrons it does not have. It only has 6 electrons. So definitely this is electron deficient. So we'll say that yes, this is electron deficient. So this bond will shift here, and hence the structure is going to be, this is CH2 double bond BH2. Boron did not had any electrons before, but now it has, that's why it will have a negative charge here, right? Now what about this one? Let me just confuse you a little bit. Tell me, will it show any kind of resonance? This is electron rich and it has lone pair of electrons. Will it show any kind of resonance? Right? Okay. Third one, fourth one. Yes, Sai Krishna, Ravi, Manoj, Giri, Rauma, Ujjwal, JEE aspirant, tell me about it. Will it show any kind of resonance or no? Fourth one. Yes or no? No, no, okay. Now, for this you should have a knowledge about inorganic chemistry. I'll tell you about, I'll just, one point I'm going to recall, right? You tell me I'm talking some sense or not. Have we learnt about this thing that first element of all the groups of P block, first element of all the blocks of P block will not have any d orbital. Do you remember in P block, we understood this concept that first element of every group will not extend their orbit, will not extend their covalency. In every single P block, 13, 14, 15, 16, every group we have learned, that boron, carbon, nitrogen, oxygen, they won't be able to expand their covalency. But second elements can. Why? Because they have vacant d orbitals, right? So can I say this chlorine is fluorine, it is the second element. So can I say chlorine is actually electron deficient? How, ma'am? It has lone pair of electrons. It is electron deficient because of its vacant d orbitals. Because of its vacant d orbitals, that's why definitely back bonding will exist here. Right? So in all these cases, back bonding will exist. Right? Okay? Yes, Manoj, very good. Right? Understood? Very good. Now let's see. Firstly, we talked about in types of resonance, we talked about first category, that is back bonding. The second category here is double bond and p orbital, right? So what is that? This actually will give you four kind of things. First is double bond, single bond, negative charge, like you have negative. Double bond, single bond, positive charge, positive. Double bond, single bond, you can have lone pair also here, lone pairs, or you can have a double bond, single bond, instead of vacant orbital is there in this only, you can say one electron. You can write here one electron. Okay? You can write here one electron. Okay? You can also have fourth one, double bond, single bond and free radical. So these are the four things that is possible. First is, one is carbanion, other is having carbocation, other is lone pair, next is free radical. Okay? So these are the four things: double bond, single bond, free radical, double bond, single bond, lone pair, double bond, single bond, positive, double bond, single bond, negative. Right? These are the four things that we have. And how we are going to do this? Simply, now double bond, single bond, lone pair. Lone pair will shift and bond pair will shift here. Lone pair, whenever lone pair is shifting to a double bond, it will always carry a positive charge here, because now it has become electron deficient. That's why A will have positive. And bond pair to negative. Why not lone pair? Tell me why I have not written, instead of negative, why I have not written lone pair? Because beta, whenever a bond breaks and the charge, and whenever a bond will break and the electrons are on that atom, it will always be a negative charge. It cannot be a lone pair, right? So bond pair to double bond, lone pair to double bond, lone pair to bond pair to negative charge. Okay? This is, whenever, see, one difference you will see. Can you see this major difference here? Now that's why I taught you that conceptual knowledge is very important for you to understand organic chemistry. Otherwise you are just cramming things, and then what happens, ma'am, we don't understand, ma'am, organic chemistry, it's very tough. Now beta, tell me one thing. Tell me bacha one thing. Tell me one thing. Lone pair, it is here, lone pair is shifting, here negative charge is shifting. Here after shifting you have positive on A. Here after shifting you have neutral on A. Can you tell me the difference? Why it is so? See, a lone pair is actually like you have 20 rupees of your own. Not 20 is too less. Let's say you have 2000 rupees in your pocket, right? And you have just lost 2000 rupees. Now what will happen? You will feel like clueless. You'll be like, oh my God, those 2000 rupees I don't have now, right? Someone takes out those 2000 rupees. So you will feel deficiency, right? That's why whenever those two electrons are of your own only, then if someone takes out those electrons from you, you will feel very electron deficient. But here one electron, when you have A negative, one electron is of A, one electron it has gained from someone else. That is the reason when it loses those two electrons, now you have 2000 rupees. Let's say only 500 rupees were your own and 1500 rupees were of someone else. Now you lost it. You'll be like, okay, but only 500 rupees were of my own, 1500 rupees were of someone else. You will feel less electron deficient. You will not be like crying all day alone, right? So that's why here you will not have positive charge. Simple, right? Okay. Then also another way is that you should remember that electrical neutrality should be maintained. Here it is overall positive. Sorry, it is overall neutral. Here also it is overall neutral. Here it is overall negative. Overall negative. Here if you see double bond, single bond positive, this bond will shift here. When this bond is shifting here, this will develop a double bond here, right? Okay. And here this will occupy a positive charge. From where the electron is shifting, that will occupy a positive charge. When you have double bond, single bond, free radical, again the same thing. But here it is a homoleptic cleavage. Homoleptic cleavage means that the electron will shift like this. One will shift here, one electron will shift here. One electron from here, one free radical, that will make a double bond, and one electron has shifted here, that means here you will have a free radical, and that's how double bond, single bond, p orbital works, right? Okay. Yes. Actual reason is also same, no? That here what you have, these two electrons are like lone pairs. So whenever it loses lone pairs, it feels electron deficient. And here one electron is of this A, one electron it has gained from someone else. That is why when it, see, simple thing is, whenever you see a bond, in a bond always one electron, so it shares only. So sharing one electron is very normal thing for an atom. But sharing two electrons, it goes crazy. It is like, why I have to share two electrons? Here it is sharing two electrons. Here this A has to share two electrons. That's why it is positive. Here this two electrons, one electron is of A, one electron is of someone else. So when it gives these two electrons to in a shared covalent bond, that means one electron is of, wait a minute, that means here one electron is of A and one electron is of C, is of something else, and here two electrons is of A only. That is the reason here it will develop a positive charge, because any atom is not prepared to share its two electrons in a single bond. Here this particular atom is doing that. Here this atom is not donating its two electrons. Here that one electron is already of someone else, right? Okay, get it? Yes. Yes. Lone pair is a part of atom but not charge. Yes. Very good. Right? Okay, I think we have covered this one here. Right, now we will be doing, let's do some examples, okay? Let's do some examples, right? So let's do some examples. You have CH2 double bond CH, then you have NH2, right? You have CH2 double bond CH, you have CH2 positive, right? Then you have CH2 double bond, this is CH, this is let's say double bond, single bond, let's say we have CH2 free radical. Let's say, have we discussed about negative charge? No. Let's see. Okay. Now I'm going to draw those examples in front of you. Let's see if you can do that as well or not. So always remember lone pair to bond pair to negative charge. So that's why here nuclei will remain on the same place. Sigma bonds will remain on the same place. Right, so that's why I'm not going to change any nuclei or any sigma bond here. Right, that is going to remain on the same page. Right, so that's why what we'll be doing, This lone pair to bond pair, so this is a double bond, and bond pair to lone pair, this is a negative charge. Whenever lone pair to bond pair happens, always it carries a positive charge. Whenever from lone pair it is getting converted to bond pair, right? Now here it is, double bond is shifting here, so that's why directly what we will say that here you will have a double bond, and that's why positive charge will be over here, and that is your okay. Giri, tell me what is the problem that you are getting, right? Yes. Now, this is double bond, single bond, free radical. I'll just slow a little bit if you're not able to understand. This is homolytic cleavage, right? One electron will move here, right? Chalo, I'll just draw. Wait a minute. Yes. So, nuclei means these atoms will stay as it is. Sigma bond will stay as it is, right? Sigma bond will stay as it is. These CH2, they will stay as it is. Sigma bonds will stay as it is, right? Nuclei and sigma bonds, guys, they are staying as it is. We are not going to change the nuclei, or we are not going to change the sigma bonds, right? Okay, right? Rama Raju, that's not possible. If that is so, I'll talk to the team, right? Yes, don't worry, you will definitely get your gift. Okay, don't worry about that. I'll just confirm that who is the AIR 4 in the MVSAT, and I'll let you know about it, right? Okay, yes. So now here we can see that this particular negative charge will shift here and this bond will shift here. Whenever negative charge is shifting, right, this has a double bond here, right? Wait a minute, negative charge to bond pair, and bond pair to negative charge. This is the form. Here homolytic cleavage, that's why here it will be a double bond here, right? And here it will have a free radical here. And that's how you will have this. Tell me, is there any problem that you are facing in drawing the resonating structures? Right, again I am telling you the same sequence I am following here. This page you should be able to understand, right? Other things are quite simple here, right? Double bond, single bond, lone pair to bond pair to negative. Negative charge to bond pair to negative. Then in this case, double bond will shift here and here you will have positive, here double bond will shift here and here you will have free radical. Okay, right? Any problem, guys? Any problem? Got it? Chalo. Now let's see the next one. Right? Now here, next thing, guys, what we have is, wait a minute, let's see the examples of resonance here. If you see the examples of resonance, right, this is double bond, this is positive, this is negative, right? So what exactly you have here? First thing is double bond will shift. This is actually, ignore this positive here. Why this is negative and this is positive? Whenever oxygen has single bond, it acquires negative charge. Whenever oxygen has two bonds, it is neutral. Whenever oxygen has three bonds, it is positive. That's why here you have positive, here it is negative, right? So now this bond will shift here, double bond will shift here, and carbon ion will be shifted here. That's why this will be the case here, right? Okay. Now because there are two oxygens, right? There is -1 charge, total oxygens are 2. That is why each of them will have, in the resonance hybrid, what you will see, each of them will carry -½ charge here, because these two are sharing that -1 charge. So the charge, see the formal charge that you have, that is charge divided by atoms. Okay, so this is, wait a minute, charge divided by atoms, right? Charge is -1, atom is 2, so it is -1/2. Okay, so this is going to be -1/2. 1 by 2. Right everyone? Acha, now let's talk about resonance, double bond, single bond, double bond. This is double bond, single bond, double bond, single bond, then single bond, double bond. So if you see this here in this case resonance will be there, right? This is a case of alternate resonance. Wait a minute, have we discussed about alternate bonds? We have not discussed about alternate bonds. So let us just discuss about alternate. Third type of resonance is alternate double bond. Alternate double bond resonance. First was back bonding, second was double bond, single bond, p orbital, third is alternate bonds. In alternate double bonds, what will happen in this case? This bond will shift here, you will have this kind of situation. And here, because this bond has shifted, that's why here you will have positive, and here you have gained a bond. Wait a minute. Here this bond will shift here and this bond will shift on this carbon. That's why here you will have negative. That is alternate single double bond resonance, where this bond will shift here, this bond will shift here, because this carbon is getting electron deficient, it will have positive. Because this carbon is having one more electron here, that is why it will be carbanion, that is negative, right? Okay, tell me, right? So in the first case you have alternate double single bond resonance. In the second case, can you see where you can see the resonance? Double bond, single bond, double bond. Here I can see resonance is there. But then it is single bond, double bond. So here it is not a complete resonance. Resonance is only there in this particular thing. Double bond, single bond, double bond. It is not extending up to like full ring, full chain. It is not extended in this full chain. The resonance that you can see is only over here. So this is the only point where you can see the resonance, right? Resonance, right everybody? Understood that or not? Yes. Next is, if you see this one here, tell me about this one. This is the first and this is the second. Everybody do let me know which one where it will show the resonance. Single bond, double bond, double bond, single bond, double bond, single bond, single bond, double bond, single bond, single bond. That means here the resonance is breaking. Double bond, single bond, it will not show any resonance. Double bond, single bond, double bond, it will also not show any kind of resonance. Double bond, single bond, no resonance. So only resonance that you can see is over here, right? Only resonance that you can see is over here at this particular point, right? Okay. Yes, first one does not show resonance at the end. Very good, very good. Now let's see, what about this one? Will it show any resonance? This bond will shift here, right? So if you see this here, right, I'll just not change the nuclei here. This bond has shifted here, right? That's why here positive will be shifted here, and that is the resonating structure that you will draw, right? Okay, that is the resonating structure that you will draw. Right everybody, got it or not? Do let me know in the chat box everybody. Do let me know in the chat box everyone if that is clear to all of you. Right? Okay. Next one, let's discuss about this thing here. Let's see. Very good. Duration is, guys, I think by 12 will be like the class will end by 12, 10 or something like that. Okay. Now let's see the stability of resonating structures. Okay. So what you have here, what you want me to repeat? Yes, Sai, what you want me to repeat? This one, double bond shifts here. That's why I have drawn a double bond here. Now this carbon is not electron deficient, but now this carbon is electron deficient. Always in this case what happens? Double bond will shift, and from where the double bond is shifting, that will have a carbocation. Okay? Yes. So next is stability of resonating structures. Let's talk about that. Stability of resonating structures, everyone. Are you ready for that one? Stability of resonating structures, everyone ready? Stability of resonating structures. So here what we have. First thing is neutral is always more than charged. Okay. So first thing is always and always neutral is more than charged, right? The neutral one, the one that is a neutral molecule will always have, I'll also show you the examples here, right? So a neutral molecule will always will be more stable, and here I am talking about where nuclei are same. This is the resonating structure of same molecule. For the same molecule, if there is a neutral molecule, then neutral molecule will be more stable as compared to charged. Then if all of them are charged or all of them are neutral, then stability will be dependent upon number of pi bonds. More the number of pi bonds, more will be the stability. That is directly proportional, right? Then if all of them has same pi bonds, then you will see the third step. You will see the negative charge, where the negative charge is more stable. So remember that negative charge is more stable down the group also and along the period also. As you go down the group, the stability of negative charge increases. As you go along the period, stability of negative charge increases there as well, right? Then more charge separation, right? If charge separation, let's say you have a point where this is the point where, let's say, this is positive, this is negative, and you have a point where this is positive, this is negative. So where you can see more charge separation, here you can see more charge separation. So more charge separation means less stability, so that is why this is going to be more stable, right? Okay, so they are inversely proportional. The last one is for benzenoid ring, stability is defined by number of rings. More the number of rings, more will be the stability. And for separated and fused rings, separated rings will have more stability. I'll just give you the examples here. Wait a minute. Firstly, let me give you the examples of the last point that we have discussed. Here is the first and here is the second question. So if you see this here, right, which one will have more stability? So these are benzenoid rings, where benzene rings, right? Okay, so where benzene rings are fused together, right? So in that case, more the number of rings, more will be the stability. That means the stability will be like this, right? Okay. And in these two cases, what you will see, that always separate rings will have more stability as compared to fused rings. Okay, right, everybody? Now let's see this thing here. Which one is most stable resonating structure here? Who will tell me about this? Which one is most stable? Firstly, tell me, is there any resonating structure which is neutral? Is there any? Firstly, whenever we talk about the resonating structure of same molecule, firstly we'll see which one is neutral here. Is there any resonating structure that is neutral? Yes, everybody, tell me about it. Is there any resonating structure that is neutral? Any resonating structure that is neutral here? Array, tell me, guys, tell me. Wake up and tell me. No, right? There is no resonating. I have not asked you a very big question. You can easily answer that. Which one is neutral? Ma'am, none of them is neutral, ma'am. All of them are negative. So second case was, if all of them are charged, then we'll see the number of pi bonds. Pi bonds, here also you have 3 pi bonds. Here also you have 3 pi bonds. Here also 3 pi bonds. Here also 3, 1, 2, 3, 3 pi bonds. So all of them has 3 pi bonds, that means based on pi bonds also I cannot tell the stability here, right? Now based on pi bonds also you can't tell the stability. Now let's see what is the other thing that we can say. What is the other thing, guys? Based on pi bonds also you can't tell the stability. Now third thing was stability I can't define based on, I'll define it on based on the negative charge where it is, right? Here negative charge is on carbon, here it is on carbon, here it is on chlorine, and here it is on again carbon. Negative charge is more stable along the period and round the group, and we know that chlorine is more electronegative as compared to carbon. So the stability of negative charge on chlorine is more, and that is the reason C is going to be the correct answer. It is going to be most stable here, right? Very good, Vasant. C is going to be most stable, right? So you will not directly say C is more, you will not directly say that negative charge is more stable. First you will see neutral, then you will see pi bonds, then you will see negative charge stability. You have to follow that sequence always, right? Okay. Now let's talk about equivalent resonating structures. So what are equivalent resonating structures, guys? Yes, periodicity. Yes, very good. Periodically you will see. Now, equivalent resonating structures are the ones that look alike. So when you see the structure, when this bond shifts here, this you will have a double bond here and you will have a positive here, right? And when you have a double bond here, it will shift here, you will have a positive here, right? And that's how you will see all of them has double bond, single bond, free positive, double bond, single bond, positive, double bond, single bond, positive. So all are equivalent structures. You can also say, for example, you have this. This will shift here, this will shift here. It will have R, CO negative double bond. Can I say both of them are equivalent structures? Yes. This is carbon having double bond O and single bond O negative. Carbon is having double bond O and single bond O negative. That means they are equivalent structures. And equivalent structures have same energy and they make a very stable resonating structures, right? They make very stable resonating structures, right? Okay? Right? Okay? Yes, everybody. Tell me. Now let's see crossed and extended resonance. If you see crossed and extended resonance, in case of crossed resonance, it's like you are on a bike and your one leg is on, let's say you are, this is you, this is like your one friend, this is your another friend, right? And you're doing some stunt, which I will never advise, right? Let's say I will not say you because you're not that psycho to do these kind of stunts, isn't it? Or you are. If you are, then you're really stupid if you're doing these kind of stunts. So let's say you have two bikes, right? Not you, someone else, someone psycho person out there, right? Very unstable person, right? What they are doing, one leg on one bike, other leg on other bike. Same situation here, right? Here what is happening? Either it can show resonance like this or it can show resonance like this. That is a crossed resonance. Either this resonance it can show or this resonance it can show. But in this case, if you see, this can show resonance like this, this double bond will shift here, then this will shift here, right? So it is an extended resonance. Double bond, then double bond, single bond, positive. It is showing mixture of two resonances, right? In an extended form, that is extended resonance, right? Now the question is, which one is more, like, what you are saying, Ujjwal, what you want to understand, tell me. Huh? You are like talking, I am not able to see any other person that you are talking to. I don't know what you are saying. Which definition we should learn? Huh? Tell me. Now, crossed is more stable or extended is more stable? Tell me, you are sitting on one bike, right? You are sitting on one bike and you are going somewhere. That is more stable, or your one leg is on one bike and other leg is on other bike. That is more stable. Or I can say simply, if you follow one teacher religiously, or if you follow one book religiously, you will be more stable as compared to when you are switching from one book to other book, switching from one teacher to other teacher, will become really unstable, right? So what exactly is there? Cross conjugation is not stable, right? When you are focusing on 3-4 things at a time, you won't be able to do even a single thing with full potential. If you are focusing on dedicated on one thing, like Arjuna, right? Focus on just one thing is there, right? Then you will be able to conquer that always. You will be able to, have that thing. Why? Because your full focus is in that thing. So that is extended conjugation. That is going in only one direction. Cross is moving here and there, confused state. Cross means confused. Confusion is always not good, right? So that is why one bike only, right? So cross conjugation is always less stable. We can say extended structures are more stable as compared to crossed structures, right? Okay. Now if you see this thing here, double bond, single bond, double bond, either it can show resonance here or it can show resonance here, right? Okay. But in this case, it will show resonance like this, double bond, then it is shifting here, then it is shifting here, right? Here resonance, either it can show resonance like this or it can show resonance like this. This is cross. So obviously extended is more stable as compared to cross conjugation, right? Okay. Extended is more stable as compared to cross conjugation. Okay. Okay, Ujjwal. Okay. No, nothing? Okay. Tell me. Great. So, now let's see dancing resonance. Another type of resonance is the biggest topic here, right? That's why I'm investing that much time on resonance, right? Next is, yes, everybody, that's why this is a detailed one shot. I'm not hurrying up things. Dancing resonance is, let's say, in this kind of situation, right? Wait a minute. Yes. Wait a minute. Wait a minute. Wait a minute. I forgot what was the structure. I'm so sorry. Yes. My bad. I'm so sorry. So, this was the structure. I'll just draw it with the help of this one, right? Okay. So, actually, this was the structure. Here you had this positive, okay? Here you had this thing. And this is very stable resonance. I'll tell you why it is called as dancing resonance, okay? Yes. So here what you will have in this kind of situation, because of angle strain, what will happen here, this particular bond will shift here, right? This particular bond will shift here, and the resonance that you will see is this kind of resonance, that it will make this kind of structure here, right? Okay. or this might shift here as well. This might shift here as well, and it can also make another kind of structure, that is this. ठीक है? Okay? I'm doing it wrong. Wait a minute. So sorry. Two kind of structures are possible. First is this, because of the angle strain, this particular bond, this sigma bond can shift here, right? And this can make, because of the angle strain, this will happen. This will make a structure like this because it has shifted from this side. It will be a positive here. Yes. Now this is the structure. Yes. Okay. Or this can also take place like this. This bond can shift here as well, right? So two things are possible. This bond can also shift here, and this can also make a structure like this. This will stay intact. This will stay intact. This will be a double bond here, and this will be a positive charge here, right? So that will stay intact, and this is your overall structure, as you can see. And it is a very stable resonance. It is even more stable than back bonding. This happens because of the angle strain of a cyclopropane ring, right? That is why this resonance takes place. And why it is called dancing resonance, as you can see, the here sigma bond can break, or here it can break, and here just like you dance on one leg, it is like standing on this, like you're not standing, it has just one bond here, and here it is having just one bond. So this resonance is such that either this bond can break and it can have a bond here, either this bond can break and it can have a bond here. So that is the dancing. It's like you're in the dancing situation where electrons are dancing here and there, and that is why it is called as dancing resonance. The picture is like that, that's why it is called as dancing resonance, and it is even more stable than the back bonding, highly stable, right? Okay. Next is the bond length. How do we define the bond length based on resonance? Here we see that there is no resonance here, no resonance. In this case, there is no resonance, right? But in this case, you can see the resonance, double bond to this side, and this can shift here. So it can have a resonance structures like CH2. This will shift here. This is a double bond, and this will shift here. So it will have a positive charge. This will be H. So that means this particular CO bond will be not fully double bond. It will be a single bond. This is a partial double bond. Because of resonance, this is a partial double bond, and this CO bond is a pure double bond. Now if you see that we know that single bond length is more, then you have double bond, then you have triple bond. But in between you have partial double bond, right? Partial double bond length is in between single bond and double bond, and that is why if you see the bond length here, this is, if I define, this is Y and this is X, definitely Y is going to have more bond length as compared to X, right? Okay, that is the concept of bond length. Okay, yes, yes, I cyclopropyl, ma'am, yes, cyclopropyl. Cyclopropyl is going to show you dancing resonance, but double bond is not there. How can it show resonance? Again, because of angle strain, the ring is very small. 3-membered ring, cyclopropyl ring is not very stable, and you are giving it a positive charge as well, so it is not at all stable ring. And that is why this resonance is quite stable, because of angle strain this is existing, right? Okay, right everybody? Chalo, understood? Right everyone? Yes. So let's see the next part here. Let's see some questions. Here the question is, which of the following molecule is least resonance stabilized? Least resonance stabilized, you should tell me, you should be able to tell me least resonance stabilized. Yes, everyone. You can say angle strain is like orbitals are repelling each other, right? See, simple thing is, this is a cyclopropyl ring, so this should be sp2, this should be sp2, this should be sp2. They should exist in one plane, so they should have 120-degree angles between each of them. But that is very difficult to achieve, 120-degree angle in this case. That is why angle strain occurs, right? And that is the reason the bond breaks, okay? That's a different kind of resonance. That is not happening because of double bond, right? That is not happening because of double bond, right? Okay. Now tell me, which of the following is least stable, least resonance stabilized? If you see, this is double bond, single bond, lone pair, single bond, double bond, single bond. All over complete conjugation is there, so it is quite stabilized. This is double bond, single bond, double bond, single bond, double bond, single bond, double bond. So it is also quite stabilized. Again, this is double bond, single bond, double bond, single bond, double bond, again quite stabilized. Here in this case, double bond, single bond, double bond, double bond, single bond, double bond, and here single bond, single bond. So here double bond, single bond, double bond, single bond, single bond. That means overall complete conjugation is not there. It has cross conjugation. And that is the reason this is least resonance stabilized, okay? Because of cross conjugation. Tell me, is that clear everyone? Why it is least stabilized? It is because of the cross conjugation, right? Okay. Next is 2021 question. Which among the following resonating structure is not correct here? Right, so you have to tell me that which of the following is right, is not correct in this case, right? So you should be able to draw the resonating structures here, right? So if you see this particular compound here, not correct means least stabilized. If I take any of the structure, let's say I am taking this as my structure. Double bond, this can exist in double bond, this can exist in positive negative, N positive, O negative, N positive, O negative. See, 3 plus minus charges are there. Here if you see, here I can see one thing, which of the following resonating structure is not correct. You can see one thing over here, that in this case you have positive, negative, and then here also you have negative, right? And if you see this, on this nitrogen you already have 4 bonds. 4 bonds are there, that is why it has positive. 1 oxygen negative, that's why 1 oxygen is negative. Here 4 bonds are there, that's why it is positive. 1 double bond oxygen, 1 is O negative. Here also it is same, here also it is the same, right? But here can you see one thing, nitrogen is actually linked to 4 bonds, but here it is linked to 1 O negative and 1 O negative. So one positive charge is directly linked to 2 negative charges. That will make it very unstable here, right? Okay. Yes. Now, if you see this one here, right? If you see this one here, this is not very stable, right? Because of these charges here, but separation is good. Acha, if you see here, positive is next to each other. In any other case, you can't see positive next to each other. This is positive negative pair is there, negative positive pair, positive negative, positive negative, positive negative, right? So all of them are positive negative pairs. So I can say this one is actually least stable, right? And after this you will have this one, right? these two are still stable as compared to these two structures. So this one out of them will be least stable because same charges will not be there in the adjacent positions. Same charge cannot be there on the adjacent positions. Okay? Yes, everyone? Now let's see resonance and mesomeric. Now we are moving towards more things, right? Okay? Less sound is there. Okay? Less sound you are saying. Chalo. Okay, let's test this now if we have less sound or not. I'll surely, if I feel that less sound is there, I'll surely increase this. Okay? Less sound is there. Okay? Less sound you are saying. How come this is less sound? Huh? How come this is less sound, guys? Tell me. Like, really, kuch bhi, you're just saying things. You need to, you need to check your ears, or you need to see the speakers, whether they are working or not, because my vocal cords are literally working a lot, right? So, resonance versus mesomeric effect, if you see, in case of resonance, guys, what we have is double bond, single bond, double bond, single bond, double bond, right? That is not because of some external group that is linked to it. In case of mesomeric effect, the resonance is there, but this is because of some external group that is linked to it. Like you have OH here, because of OH, the resonance is going to shift, and that is why it is not only a resonance, it is a mesomeric effect, right? So the subtle difference between, right, resonance and mesomeric effect is, in resonance you don't have any external group. In case of mesomeric effect, you have a external group, because of which it shows two kind of resonance. So all mesomeric effect are resonance. All, like, mesomeric effect is under the category of resonance only. All mesomeric effect will be resonance, but all resonance are not mesomeric. So this is not mesomeric, this is not mesomeric effect, but this is also resonance effect. This is, we can say this is resonance, or you can also say this is mesomeric, right? Okay. Next is, let's see what are the things that shows plus M or plus R effect. Let's see that. So guys, if you see mesomeric effect, right, in this case, if you talk about mesomeric effect, in that case, always you will have a group that has lone pair of electrons attached to it, right? So lone pairs, single bond, double bond, lone pairs will shift here, this will shift here, and we can say always and always you will have a group which has lone pair of electrons attached to it, right? But in this case, you will have the attachment of a group that will be connected to more electronegative element. Here X is more electronegative, and in this case, because this is more, and this will be connected by multiple bond, and this will always show minus M or minus R effect. That means electron withdrawing. So this one is electron donating group, electron donating effect it will show. This will show electron withdrawing effect, right? So here you will see what kind of resonating structures. Here always remember one more thing here, right? Wait a minute, let me just show you the examples here. The examples of plus are, because they all have lone pairs and they are not connected by multiple bond to something more electronegative, so they will show plus M. Here it is connected by multiple bond to a more electronegative. It is connected by multiple bond to a more electronegative. It is connected, it is connected, it is connected, it is connected. So whenever they are connected to some more electronegative element by a multiple bond, that is showing you minus M effect, right? And you will see this when you draw these structures that, wait a minute, definition is plus M effect, it is operates on pi bond, right? Permanent effect, these are distance dependent, these are actual charge development is there, There is not partial charge, there is actual charge development here, right? Now plus M effect groups dominates para electrons to a conjugated system. Group withdraws, this is not para, this would be pi. Wait a minute. Let me just, pi electrons, right? Pi electrons will take care of the pi electrons here, right? Okay, will take care of the pi electrons here, right? Acha, now see one thing. What you will see now, when you will do these structures, I'll just show you all the structures. If you see, this will shift here, this will shift here. So what exactly you will have? You will have negative charge on the para position. When you start drawing on the ortho, this is the ortho position, right? Wait a minute. Okay, this will move here and this will move here, and hence you will have negative charge here, double bond, and this is double bond OH. That means, guys, can you see one thing? That always you will have negative charge on the para and ortho position in case of plus M. And that is the reason I'll just simply write ortho and para. You will have negative charge. Here ortho and para, you will have positive charge. And on meta, electron density will be more. That's why electron density is more. That is why we can say that if you have a electrophilic substitution means you will have a reagent which will react, which will attack on the more electron dense position. So when you have these kind of groups, then it will show ortho-para directing, ortho-para products. But if you have minus M effect, then it will show meta product. Okay, right? That's why phenol, aniline, they all shows anisole, they all gives you ortho-para products on electrophilic substitution, right? Okay, so and always remember that in case of plus M, they are always activating in nature because they are always giving the electrons, and these are always deactivating in nature. These are always deactivating in the nature, right? They're always deactivating in nature, right? So donates the electrons, so plus M are always activating and they are ortho-para directing, and minus M are deactivating and they are meta directing. But there is one important exception here, that is this exception. Let's talk about this exception, everyone. Let's talk about this exception, everyone, right? Okay, yes, minus I and plus M groups. Yes. Now, if you see this here, what about these exceptions? In the case of exceptions, what you will have? In the case of exceptions, always remember that halogen, see all the groups that shows mesomeric and inductive, in all the groups, mesomeric effect is dominating. So we don't even look at inductive effect. But in case of halogens, inductive effect is dominating. See, halogen shows you minus I effect because of electronegativity and plus M effect because of the lone pairs. But in this case, plus M effect is more dominating, minus I effect is more dominating as compared to plus M. And because of minus I effect is more dominating, they are showing which category? They are showing, because of this, they are deactivating in nature. So you can say minus I, due to this, they are deactivating in nature, right? So because of their minus I is greater, minus I is due to high electronegativity and plus M is due to presence of lone pair. Minus I is greater, that is why these compounds are, that is why halogens are deactivating because of minus I. I'll just write it here, it is deactivating because of minus I. But because of plus M, but because of plus M, they are ortho-para directing. This is because of plus M. So there are very rare groups like halogens which shows you minus, which are deactivating also, and they are ortho-para. Usually ortho-para directing are activating, meta-directing are deactivating, but halogen is the only group which is ortho-para directing also, and also it is deactivating in nature. Okay, right? Okay. What they activate the benzene ring. Okay, they activate the benzene ring here. So if you see, when it is donating the electrons here, it is donating, that means it is making the it's like someone is sitting there, he wants to study but he is not able to study, and I push them, I am like, hey, why not studying? Teacher is pushing you to study, we are activating you, right? So they are showing resonance because of this group, even more resonance, even more delocalization of electron is there, right? That is activating. Here it is withdrawing the electron here from this pi cloud, that is deactivating, right? Okay, tell me, clear everyone? Let's do some questions on this JEE 2025 question, and a very, very important question based on this concept only. Let's understand this. Let's understand this. If you see, identify the correct statements here. First is they are asking you correct statements here, JEE 2025. First is OCH3NH. Now, the thing that I told you, if you have a compound that is having lone pair and it is not connected to any multiple bond with more electronegative, that will show plus M. So that plus M means it is activating. So this is showing plus M, and this is also N, this is H, this is C double bond O. Definitely this has lone pairs. Now you will say, ma'am, but this is connected to, I am not talking about the atom that is next to it. I am talking about only the atom that is connected to benzene ring. If it is connected via multiple bond to something else, it is not, so it will also show plus M. So this will also show plus M. So first statement is obviously true here, so we can say that is true. Next is CN and OH are meta-directing. Obviously not. OH is plus M, that is why it is going to be ortho-para directing. So this is the false statement here, right? CN and SO3H are meta-directing. That is absolutely correct here. That is absolutely true. So if you see this here, C triple bond N, see, carbon is connected by a multiple bond to more electronegative, and then SOOH. This also, sulfur is connected to multiple bond to a more electronegative oxygen. Also, it will show minus M effect. That means they are going to be meta-directing. So that is true. Activating group act as ortho-para directing groups. Yes, that is true. In most of the cases, that is true, right? Halides are activating groups? No. Halides are deactivating groups. Halides are deactivating because of minus I, they are deactivating. So we can say this is not correct. So answer will be correct statement are A, C, D. So answer will be A is the correct answer here. Okay. Now next concept is hyperconjugation. Everybody didn't check D option. A is answer. Yes, A is the correct answer. Completely enough, or should I see rows, is GOC? No, this session is enough for you, Ramya. Yes, that's why I'm making this session, because this is enough, right? This is enough, right? So let's see this. Let's see this hyperconjugation effect. Everyone, let's see hyperconjugation effect here. Quite a simple effect, one of the simple effects here, hyperconjugation effect. Let's understand that. So in case of hyperconjugation effect, we talk about delocalization of sigma bonds, sigma electrons. In resonance, we talk about delocalization of pi electrons. Here we talk about delocalization of sigma electrons, right? Okay. So let's talk about this. If you say the delocalization of sigma electrons, it involves delocalization of sigma electrons, CH bond of an alkyl group directly attached to an atom of unsaturated system to an atom with unshared p orbital. So it is a permanent effect. We are saying it's a permanent effect. It is not dependent on anything else. It is also known as no bond resonance, Anki-Merrick effect, or Nathan-Baker effect. These are the other things. So let's see the definition again. It involves delocalization of sigma electrons of CH bond of an alkyl directly attached to an atom of unsaturated system or to an atom with unshared p orbital. That means either this can be a carbocation or this can be a double bond, anything can be there. So there is a system, I am calling it a system. So to the system, when you have the attachment of CH, what exactly happens here? This bond shifts here, right? And here what you have under hyperconjugation, what you have, that system stays as it is, right? And here you have a double bond and this becomes H positive, right? I'll give you some example about this one. Let's see, that system is a carbocation, right? So this has CH, CH and this is CH. So what will happen, this particular bond will break. I am just drawing it over here only. This bond will break. You have this bond will shift here. So what you will have here is you will have a double bond and this will give you H positive here, right? And that's why this positive charge will not be there. This is a hyperconjugating structure, right? This is a hyperconjugating structure, right? Tell me. So what exactly has happened? Here, this sigma bond has shifted. Shifting of sigma electrons are there. That is why it is called as delocalization of sigma electrons. Pi electrons we are not moving here. Why it is called as no bond resonance? Because you can see resonance is existing, but that is because of no bond. So here another situation can be that this, instead of this bond can also shift here, or this bond can also shift here. So that will give you different hyperconjugating structures like this. Double bond, if you have this bond is shifting, so this will be H positive, this will be double bond. If let's say this bond is shifting, then this will be CH2, this is double bond, this is H and this is H positive. So many cases are possible in this case, and that depends upon the hydrogens. What are those hydrogens? See, if this is the main system, then can I say this is the alpha carbon here? So how many hydrogens are connected to the alpha carbons, that will tell you the hyperconjugating structures, right? So here this is alpha carbon, 3 hydrogens are connected here, so 3 hyperconjugating structures are there. And more is the number of these, more is the number of hyperconjugating structure, more will be the stability. So what is the condition? Condition is alpha carbon should be sp3 and it should have at least 1 hydrogen. So if I say alpha carbon is sp3, that means if I say you have carbocation, this is C double bond, this is CH2. This is having, it is connected with 1 phenyl and 1 phenyl. Tell me, will this show any kind of resonance or not? Resonance means, will it show any kind of hyperconjugation or not? Will this show any kind of hyperconjugation or not? No break will be there, guys. No break will be there, right? No break will be there, otherwise we will not be able to complete this, right? Okay, so let's do it. Okay, tell me, will there be any kind of hyperconjugation? No. Because this is also sp2, this carbon is also sp2, this carbon is also sp2. First condition is not followed, this is not going to show any kind of hyperconjugation. Now I am giving you one more example here. let's say you have an example that is, let's say you have a question that is, this is C, this is CH3, this is CH3, this is CH3, and this is one phenyl here, this is one phenyl here. So I'll just draw the phenyl rings as well here, right? Tell me, will this show any kind of resonance, any kind of hyperconjugation? Tell me guys, will this show any kind of hyperconjugation? Will this show any kind of hyperconjugation? Yes or no? Shared, the slides will be available. Yes, definitely Ramya, the slides will be available to you. Don't worry about that. Right? Yes, the slides will be available to you. Yes, tell me, will this show any kind of resonance or not? Everyone in the chat box, do let me know. Ma'am, if I see this, this is sp2, this is sp2, right? This is sp3, but it has, this is alpha carbon. No hydrogen is connected to the alpha carbon, so it will not show any kind of hyperconjugation again. So these two conditions has to be satisfied, only then it will show hyperconjugation. Right, so let's talk about carbon ions. So we will not draw any hyperconjugating structure. I told you how to draw it, but we'll just simply calculate the number of alpha hydrogens. Right, so here this is alpha carbon, right? Here 3 plus 3 plus 3, so it will have 9 alpha hydrogens. That means 9 hyperconjugating structures will be there. In free radicals, if you see, this is alpha and it has, wait a minute. This is alpha, na? Yes. Okay. Yes. Here this is alpha and it has 3 hydrogens, so it will have 3 alpha hydrogens. So that means 3 hyperconjugating structures are there. In this case, the main system is this one. In case of alkenes also it shows, and this is the main system. And if you see, this is alpha and it has 3 hydrogens, so it has 3 alpha hydrogens here, right? So it has 3 alpha hydrogens. What about this one, everyone? Number of alpha hydrogen will tell you the number of hyperconjugating structure, and that will tell you the bond strength, right? Now always remember, carbon double bond carbon bond length will define the number of alpha in case of C double bond C, right? C double bond C, that means in the case of double bond, right, the hyperconjugating structure will be told by the bond length here, right? That you don't have to like give that much importance. You can, even if you know this thing, even then you will be able to solve it, right? Okay, now let's see questions on this. That is JEE 2024 question. That is for the calculation of hyperconjugating structure only. How many carbons among the following show inductive, mesomeric as well as hyperconjugating effect? So till now we have discussed inductive, we have discussed mesomeric, we have discussed hyperconjugative. Let's see how many of them will show all of these things. So I'll firstly talk about inductive. Inductive, so it's not that of a big deal, right? So inductive you can see shown by all of them only, right? Let's talk about mesomeric. Mesomeric means resonance. See, resonance is shown by this one, double bond, single bond, double bond. It is shown by this one as well. This is also showing you resonance. This is not showing because there is no double bond, single bond. There is no alternate double bond. There is no back bonding. So this will not show. This will also show mesomeric and resonance. This will also show. This will also show mesomeric effect. Achha, they are specially saying that which will show mesomeric. They are not talking about resonance here. So this benzene also does not show any kind of mesomeric. Benzene shows resonance. It does not shows you mesomeric effect here. Right? This also shows you resonance. It does not show any kind of mesomeric effect. Right? This also shows hyperconjugating structures. If you see, it is not shown by this one. Hyperconjugating structure is not shown by this one. Hyperconjugating structure is also double bond next to double bond. This will show hyperconjugating structure as well. ठीक है? This will also show hyperconjugating structure as well, right? This double bond, this will also show hyperconjugate, this will also show mesomeric, है ना? This will also show inductive, right? So this is double bond, this will also show resonance, mesomeric, everything, yes. This will also show hyperconjugating. So total 4 will be there, है ना? Total 4 will be there. If you see this here, this is showing you inductive effect also because of nitrogen. It is also showing you mesomeric effect because of NO2. It is also showing you hyperconjugating, because if I consider this as my double bond, then this alpha is giving you one hydrogen here. So this is showing you all of them. This is showing you mesomeric effect here as well. This is giving one hydrogen, sorry, hyperconjugating. This is also showing you mesomeric. This is also showing you inductive. So this is also there. This, if I consider this as double bond, it has 3 plus 3, 9, 6 alpha hydrogen. So this is also showing you hyperconjugating. It is also showing you inductive because of alkyl. It is also showing you mesomeric effect here, right? So we can see all of them, है ना? Wait a minute, this one will not show mesomeric, so this will not show. So this is also ruled out. Arey yaar, wait a minute. Till now, this one is showing you. So what should I consider first? Double bond, this is also showing you. I think they are mesomeric means resonance only they are saying. Otherwise, the 4 is not becoming the answer, because this is also not showing you proper, any mesomeric effect is not there. This is not showing you any kind of resonance, right? This is not showing you any kind of inductive or anything, right? Then you can have this carbon is having, this is not showing you any kind of hyperconjugation. Double bond is not connected to any carbon, so this is not showing you hyperconjugation here, right? So this one, here mesomeric means they are talking about resonance only, right? So this one and this one, okay? So you don't have to see it in a ring, you just have to see whether it is getting affected by some outer thing here, right? So double bond, single bond, double bond is there, right? That is means mesomeric is there, inductive is there because of this alkyl, and it also has one hydrogen here, that is my hyperconjugation is also there. This I already told you, this This one, if you see this, because of this C double bond O, right? This will be double bond, this is C double bond O, it is showing you resonance, right? And because of this CH3, it is also showing you plus I, and because of this double bond is connected to alpha carbon, which is giving you hydrogens, that's why it is also giving you like hyperconjugation. So we'll say these 4 are the correct answer here, so that will be your answer. Okay, right everyone, right? Then there is, based on only hyperconjugation you have, hyperconjugation is a permanent effect. That is true. Hyperconjugation is a permanent effect. Hyperconjugation in ethyl cation, that means this kind of cation, involves the overlapping of CP2 and H1s bond with empty 2p orbital of other. Now for this you should be able to understand what exactly happens here in case of hyperconjugation. So how do I draw? Let me see if I have any. Yes, we have page. So let's see this one. We have CH2 here. This is positive. This is CH3. If you see what will happen, this carbon, right, is making 4 bonds. So this particular carbon is actually existing in sp3 hybridization, not sp2. And here what they are saying, overlapping is between C, sp2 and hydrogen 1s. It's not there. Overlapping is between, this is 1s, this is 1s, this is 1s. So overlapping, which overlapping is going to break? So what it is saying, hyperconjugation involves the overlapping of this and this bond with empty 2p orbital of other carbon. So double bond actually, so let me just form a hyperconjugating structure. So what exactly happens? This forms a, because we know that this bond will shift here. So this is C, this is double bond, this is C, this is H, and this is H here, this is H here, and this is H positive. So what we can see, actually CH involves C sp3, that means this sp3, 1s, this is 1s, this bond overlap with empty 2p orbital. This is the empty 2p orbital. This overlap is going to happen. So you have this bond, this is the sp3 hybridized bond of this carbon, and it is overlapping with a carbon empty p orbital. That's how this double bond is actually existing here. Okay, so for that you should be able to know that what exactly happens here. So this is not sp2, this is sp3. Okay, so that is why second statement is false. So we can say statement 1 is true, statement 2 is false. So that's why answer is B is the correct answer. It's a good question from hyperconjugation, right? Okay. Next guys, we have aromaticity. So let's talk about aromaticity. Right everyone? Let's talk about aromaticity. Right? In case of aromaticity, what exactly happens? The delocalization of electron in a ring gives rise to occurrence of current and development of magnetic field. That is there, that is a pure definition. So what exactly happens? You have 3 category of compounds: aromatic, anti-aromatic and non-aromatic. Always remember, till now they have not asked aromatic and the relation with paramagnetic, diamagnetic, but they can ask you that. So once we know how to get the value, whether they are aromatic, non-aromatic or anti-aromatic, right? You should be able to relate it with dimagnetic or paramagnetic. So aromatic is di, anti-aromatic is para, and non-aromatic does not have any ring current. There is no flow of electrons in case of non-aromatic, right? So ring current is there in case of aromatic, anti-aromatic. This is diamagnetic, this is paramagnetic, right? And in case of aromatic, the number of electrons are 4n plus 2 pi. In the case of anti-aromatic, it is 4n pi electrons. In case of non-aromatic, it doesn't matter, right? So now how do you firstly judge this? Firstly, you see PCC. That means you will see planarity. That means all the atoms should be sp2. Then you will see complete conjugation that we have discussed in resonance. In full ring there should be conjugation, and it should be cyclic in nature. That is PCC. Planar cyclic conjugated, it's PCC, right? Okay. So if you see this here, aromaticity, as I have told you, cyclic, planarity, presence of conjugation, compound must follow hyperconjugation here, right? Okay, so all these things should be there, only then this will exist, right? So now if I draw these compounds here, this is A, B, C, and we are going to just talk about that which of the following is aromatic, anti-aromatic and whatsoever. So how do you discuss that? So if you see A, this is double bond, single bond, double bond, all of them are sp2. Complete conjugation is there, they are cyclic, and how many electrons? 4 pi electrons, that means it is anti-aromatic in nature, right? Then guys, we have this one. In this case, I think there should be a negative charge here. This is now always remember the carbon ion. Usually what we say, carbon ion is sp3 because it has 3 sigma bonds and a negative charge, right? But when the carbon ion is delocalized, that means if you have something like this, C double bond C, CH, this negative here, then this is sp2 because this bond is shifting here and there again and again. That's why it is not at all sp3, it is sp2, right? So here it is going to be sp2, right? So planarity is there, cyclic it is, complete conjugation it has, number of electrons are 1, 2, 3, 4, 5, 6 pi electrons. That means we can say 4n plus 2 pi electrons, that means it is aromatic in nature, right? Then guys, next is 2 pi electrons, PCC is followed. 2 pi electrons, again it is it is aromatic in nature because 4n plus 2, if you put n is equals to 0, this will become 2, right? The next one is this one, it has 4 pi electrons, that is again anti-aromatic in nature. 4 pi electrons, that is again anti-aromatic in nature. It is cyclic, complete conjugation is there, it is sp2, here also complete conjugation, cyclic, it is sp2. So PCC is followed in all these cases. So it is cyclic, complete conjugation, double bond, single bond, double bond, single bond, double bond, single bond, carbocation, single bond, double bond, single bond, complete conjugation is there. How many electrons? 6 pi electrons. That means it is aromatic. So we can say, we can definitely write which of the following is aromatic, which of the following is anti-aromatic, right? Okay, tell me. Okay, Pratija, I'll really see. Inductive effect code. People may pull you down or push you up. Choose your direction. Ma'am, like this, I have made a lot. Please check in comment, topic, lesson, keywords, ma'am. Also say Shreyas, ma'am. Okay, Pratija, very creative of you, right? Acha, tell me about this one. Now, these are heterocyclic compounds which has not only carbon but other things also as the main atoms within the rings, right? Now here's something really important to learn. The lone pairs, all the lone pairs are not involved in the pi bonds, right? In calculation of pi electrons, all the lone pairs you will not involve. You will only involve those lone pairs which are involved in the delocalization. Only those lone pairs. Now if you see here this lone pair is definitely there in the delocalization. Any lone pair which is in the delocalization will not be in the hybridization. So if you check the hybridization, this will be sp2. Why? Because sigma, sigma and sigma. Because of 3 sigma bonds. There is no lone pair. Because why? Ma'am, lone pair is there, then why you're not adding it? Because lone pair is involved in the delocalization here. So that is the reason this will be shifted here, this will be shifted here. So that is why 1, 2, 3, 4, 5, 6 pi electrons will be there. And guys, that is the reason what you will have. This is 6 pi electrons. And that is the reason this will be aromatic in nature. Here you have 2 lone pairs. But if you see, only this lone pair is involved in the delocalization, this lone pair is involved in hybridization. The lone pair that is not in the delocalization will be in the hybridization. That's why it is 2 sigma plus 1 lone pair will give you 3, that is sp2 hybridized. And this lone pair is involved in the delocalization. That's why it will be 6 pi bonds these two and these two, these four, and that is why it is aromatic in nature. Okay, that is the reason this is aromatic. Now let's see the next part here. Let's see the next part here, everyone. Why, ma'am, they are not involved? Because they are involved in delocalization. One thing they can do, either they can participate in hybridization or they can participate in delocalization. If they are moving in this ring, they cannot be stable here. If in hybridization, only those electrons are involved which are sitting on that atom, which are staying on that atom. These lone pairs are not loyal to the atom. They are moving here and there. These lone pair are not loyal, but these lone pair are loyal. Only loyal lone pairs will be involved in hybridization, and that means the one which are not involved in delocalization will be involved in the hybridization. Tell me, is that clear, everyone? Is that clear? That works? Yes, everybody? Now, let's see this one. Tell me, are these lone pair involved in the delocalization or not? Let me see if you can answer this or not. Double bond, single bond, double bond, single bond, double bond, single bond. This bond is shifting, this bond is shifting. There is no role of not in delocalization. They are not involved in delocalization. They are not there in delocalization. They are not involved there. Right? So only 6 pi electrons are there, and that is why it is aromatic in nature. Oh my God. Okay. These lone pairs, if I see, they are involved in delocalization, right? Complete conjugation is there, right? So that's why we will use 1, 2, 3, 4, 5, 6, 7, 8, and these are 8 pi electrons. That means 4n pi, that means 4n pi electrons. That means these are anti-aromatic in nature, right? How to find whether they are delocalization is in the lone pair? That you will see. Okay, now if you see this here, how we will see? See beta, how you will see whether they are in the delocalization? You have to make, see, from resonance, double bond, single bond, lone pair, single bond, double bond, double bond, single bond, lone pair, like this. That means these lone pairs will be involved because they are creating a conjugation. Here these lone pair will be involved, and it will use only one lone pair, not two lone pair. When you have two lone pair, only one will be used. In this case, why they are not involved? Because it does not need, they don't need those lone pairs. They are already in a very good conjugation, right? Here, why they are using this? Because obviously they are in need to make complete conjugation. They need the lone pair help, right? Tell me. Clear? Clear, everyone? Tell me, everyone, is that clear to all of you or not? Right? Is that clear to all of you or not? Yes, students? Tell me. Pratija, I have not seen it, but I'll surely see it. Right? Okay? Tell me, guys. Okay? Now let's talk about annulenes. Now in case of annulenes, let's talk about annulenes, guys. In case of annulenes, what we are going to see, that in case of annulenes, what you have, two things are there. Annulenes, firstly, what are annulenes? They are monocyclic. Monocyclic, only one cycle is there. Alternate double bonds. Monocyclic, and number of carbon or number of pi electrons will be in name of annulene. that will be mentioned in the name of annuline, right? So number of carbons, number of pi electrons, that will be mentioned there. So if you see this here, planarities 4, 6, 14, 16, 18, that is all of them is there in the planarity, right? So if you talk about firstly, this is a trick I am giving you, right? That there are 3 non-planar rings that you have, that is 8, 10 and 12, and from there the question they ask you. Because here PCC is not followed, so that's why 8 annuline, 10 annuline, 12 annuline is entirely non-aromatic character. That means 8 annuline, monocyclic, alternate double single bond. Here it is non-aromatic. Why it is non-planar? Because it exists in tub-like structure. It exists in tub-like structure, right? Here it is 10 carbons, it has 10 pi electrons. But why this is non-aromatic? Because if I see this is planar, then they should be at an angle of 120 degree. Because of this hydrogen-hydrogen repulsion, the hydrogen-hydrogen repulsion is very high. Because of this hydrogen-hydrogen repulsion, it will cause such a high effect of angle strain that this will go out of the plane only, right? So that is the reason they are non-planar. Similarly, in this case as well, in case of 12 annuline as well, there is a high amount of angle strain. So these two are non-aromatic because of angle strain. So this question is very important, that why 8 is non-aromatic because of tub-like structure, these two because of angle strain. Other are planar in nature, then you just have to check the pi electrons, that's it. You just have to check that, right? So you just have to check the pi electrons. This is 4n plus 2 pi electrons, this is 4n pi electrons. The one, like if you see in this case 6, 14 will be aromatic in nature. If you see 4, if you see 16, that will be anti-aromatic. 18 will also be aromatic because that is in the category of 4n plus 2 pi. This is in the category of 4n pi. Okay, so this is what you should definitely remember. Let's do more questions on that, right? And you know what, in the Sigma batch though, I give students the questions as well as questions from homework. There's so much interest that we have in the batch, right? So it's such an amazing thing, right? That when you practice, actually, you know, in our batches also, we tell the students to practice more. That's why we are also giving them the test series, right? Now, why practice is so important, right? Because, you know, this is for sure that when you do some new category of question, you're going to make mistakes in that. But if you have already solved that question, right, before the exam, you have already solved the type of questions that they ask you, you know that you're not going to make the same mistake in the exam. So mistakes, you should not get feared. Ma'am, I don't want to solve the questions because I always get the wrong answers. No, you should always solve the question even if you get the wrong answers, because you have the liberty to do mistakes in the when you are not in the exam hall. But you don't have that liberty to do mistakes when you are in the exam hall, because if you do mistakes in the exam hall, you're eventually going to lose that seat. So do mistakes before the exam, solve as many questions, and definitely questions should be relevant, right? So relevant questions you can pick from PYQs, you can pick from questions related to PYQs, right? That you must do. That is very important for you, right? Okay? Yes. Yes, everybody. Half yearly exam you have, guys. Just give me a second. Give me a second. Okay, let's do this. Let's do. And I hope so you have liked the session also. And if you have not liked, that means what I can say. You are very confused and you are just demotivating me a lot, right? Don't do that, right? So let's see this. Which of the following compound is non-aromatic? Non-aromatic, which is not planar. So I can see PCC, if it is not followed, that is non-aromatic. Here PCC is followed, here PCC is followed, here also PCC is followed, and here double bond, single bond, double bond, single bond, double bond, single bond, single bond. This is complete, no complete conjugation. You will say no complete conjugation is there. No complete conjugation is there. So C is not the correct answer here. Right? Okay, everyone. So, Ari, wait a minute. No. C is the, which of the following is non-aromatic, right? So C is the correct answer. Let me just verify this again. Double bond, single bond, positive, double, then again this one, okay. No, C is the correct answer, not A, okay. That must be some mistake, right? C is the correct answer, okay. Then the correct stability order for the following species, right? Acha. In the stability order, if you see, this is negative, this is also negative here. This is 8-annuline. This is 8-annuline. Tell me 8-annuline is aromatic or non-aromatic? Ma'am, it is non-aromatic in nature. This is 1, 2, 3, 4, 5, 6. 6 pi electrons, this is aromatic. This is 1, 2, 3, 4. 4 pi electron, it is anti-aromatic. And always aromatic is greater, then you have non-aromatic. Then there is anti-aromatic. Aromatic is Q, non-aromatic is R, anti-aromatic is P. So QRP is the correct answer here. That means D is the correct answer here. Okay, and that was your 2025 question. Right? You can see this here. 2025, they have asked you this question here. Right? Okay? Yes. Good. Now let's see next question, 2023 question, that is C. Aromaticity, they ask you a lot of questions, you can see for yourself. Among the following compounds, the one which shows highest dipole moment. So for highest dipole moment, if there is any structure which is getting converting to two aromatic structures, then that will show you highest dipole moment. Right? If you see, if you break this bond, this will be negative, this will be positive. This will be aromatic then, 6 pi electron, this will be anti-aromatic. So both are not aromatic. This you can't break only. If you break this one, right? In this case again, this is so both will be non-aromatic only. But if you see this one will be negative if this is positive. Or if I say this is positive, this is negative, this will become 6 pi electrons, this will become aromatic, this will become 2 pi electrons, this will become aromatic. So we can say the answer is A is the correct answer, because when you break this, you have two aromatic rings. Two aromatic rings means that they are going to show you maximum dipole moment. So indirectly they are asking you this question. Okay? No, tomorrow we are going to do electrochemistry. Okay? Yes. Now next is electromeric effect. Let's see a small effect from where also they have asked questions. So that's why I'm going to do it. Right? So electromeric effect is, for example, you have a double, let's say you have C double bond O, this is thing, and here you are adding Cn negative. This is also C double bond O, and here you are adding H positive. Okay? So let's say you are adding Cn negative. A negative will be, because this is partially positive, this is partially negative. This is partially positive, this is partially negative. So this will be attacked here and this electron will jump here, and that is the reason, what you will have here is C, this is O negative. Now what you can see that C negative reagent attack on carbon, electron shift on oxygen. If you have hydrogen, this will be because electrons will shift here and hydrogen will get attached here. So reagent means H positive. Reagent attack on oxygen, electron shifting on oxygen. That means here the difference we can see, visible difference here. So electromeric effect is because of the reagent, and it's a temporary effect. It's a temporary effect. It only happens because of the external reagent, in presence of external reagent. When the reagent attacks, electron shifting will take place, and because of this what will happen, right? Because of this what will happen, electron shifting and reagent attack is happening at the same time. So if they are happening on the same atom, then this is called as plus E effect. If this is happening on the opposite atom, this is called as minus E effect. Okay, that is called as minus E effect. Right, everyone, tell me, let's do the next one here. That is, which of the following is incorrect statement? 2024 question, that is, electromeric effect dominates over inductive effect. Incorrect statements we are talking about. So okay, what is happening, bro? Right. So if you see this here, electromeric effect dominates over inductive effect. Electromeric effect, right? That dominates over inductive, yes. Because you know what exactly happens if there is a reagent that is attacking, then yes, that will happen in that case. Electromeric effect is a temporary effect, that is also true. Organic compound shows electromeric effect in presence of reagent, that is also true. Hydrogen ion shows negative hydrogen ion, if you can see, it shows positive plus E effect. So we can see D is the incorrect statement here, right? So D is the incorrect statement. So answer will be, and this is asked in JEE 2024. So don't ignore these small concepts. Beta, you are too early for the class, right? Chalo. Now let's do the last topic of today's class, that is stability of intermediates, acidity, basicity. Let's do these things, right? So if you talk about stability of intermediates, before that you must know that as you go along the periods or you go down the group, extent of electron donation will always decrease. Just keep that in mind, right? Along the period, down the group, that will always decrease. Now let's see stability of intermediates. That is based on Barhi. Now Barhi means back bonding, aromaticity, resonance, hyperconjugation, inductive. So always you will use these concepts and answer the question here. Let's see how. This I'll show you directly from the questions how we will apply Barhi here. Let's see it from the questions. You should know 2-3 things here. That when we talk about carbocation, if you give the electrons, its stability increases. If you take electrons, its stability decreases. For carbon ion, when you give the electron, its stability decreases. When you take out electron, its stability increases. So it's just like that. Here we are talking about money, and here we are talking about stress. Someone gives you stress, you're not happy. Someone gives you money, you are happy, right? One thing is this. Other thing is, you must remember that for a good acid, we are talking about its carbon ion. If its carbon ion is stable, it is going to be a good acid. Okay? Sleep can't resist, but it should, right? Let's do this, right? Let's do this. I'll give you some questions for homework as well. Don't worry, right? Match the list 1 with list 2. So this is a pKa value that we know that Ka and pKa are inversely proportional to each other. So that one thing you should know, right? Now if I talk about ethanol, phenol, metanitrophenol, paranitrophenol, these are the 4 compounds that we have. Wait a minute. Achha, answer, I thought it was explained, but it is not. So I'll just write it here. Right? This is pK. So if you see this here, right, let's talk about the order of Ka, that is acidity. Now you have ethanol, which is not going to show any kind of resonance, that is The reason we are going to give it least acidic. In case of phenol, phenol is this one. It is showing resonance. Meta-nitrophenol is this one. On meta position you have NO2. Para-nitrophenol is this one. Now few important things. Mesomeric effect does not operate on the meta position. So here we'll see the effects firstly. On para position you have minus I and plus M, minus M effect. On meta position you only have minus I because mesomeric effect is not operating on the meta position, and here you have phenol. So exactly what happens here, this is minus I minus M, this is minus M, what exactly will happen? This is negative, negative, negative. So as you withdraw the electrons from carbon ion, it will become more stable. So that's why this is maximum stability, then this one that it has minimum. So you will see, and then you will have ethanol. And stability will define the order of acidity, right? pKa will be opposite of that. That means ethanol is going to have maximum, right? A is going to have maximum. Then you will have meta. This is going to be minimum. Meta is going to be on C. This is D. This is B. Okay, it should be like this. A, B, C, D. A is going to have maximum. Maximum means 15. So A is 2, right? B is going to have 1. After this, then after that you will have 4. That after this, and after this you will have 3. So answer is going to be D is the correct answer. So all I did is use two concepts and we got the answer. Next few things based on stability of intermediates is this one. You will apply Barhi here, B-A-R-H-I. If you see here, then you will see that in this case there is back bonding in this case, right? Back bonding. And back bonding is highest priority, so it will stabilize these things. That's why A will be more stable as compared to B, right? Then you will have this compound here. Now this is an exception, okay? That's why I have put it here. This is an exception. They can ask you this in the exam, right? So this exception says that when you have this and this, now according to this thing, you have C positive, you have 3 methyl groups here. That means it is connected to 3CH3. Inductive effect is there is no resonance here. But in this case, you have resonance. If you see this here, you have resonance here. You have resonance here. In this case, you can see the resonance here, right? Now, it shows you 3 plus I effect. This is plus I, this is plus I, this is plus I, right? Okay. And in this case, you can see resonance. So, according to Barhi, B-A-R-H-I, resonance is more dominating as compared to inductive. So, this should be more stable. But in reality, this is more stable because 3 times inductive makes it more stable as compared to 1 time resonance, right? So, that is why A is more stable as compared to B, right? That is an exception. Okay, so I'll just... So, let's see, not that much we are left with, guys. So, let's do this. JEE Mains 2025 question, that is, which of the following carbocation is most stable? Again, we will apply Barhi here, B-A-R-H-I. So, I'll see firstly if there is any kind of back bonding here. I can see back bonding in so many cases, okay? Where I can't see any back bonding is this one. So that is obviously ruled out because here I can't see any kind of back bonding, right? So back bonding I can see here, back bonding I can see here, back bonding, and I'll see if there is any extended conjugation. Back bonding with oxygen is better because oxygen is better in giving. It is less electronegative as compared to fluorine. Fluorine is very high electronegative. So oxygen is better in giving the electrons. So that is also ruled out. So if I see this here, double bond, single bond, lone pair, single bond, double bond, then this. This is, this if I see, this shifts here, this shifts here, this shifts here. So it's a very good resonance that I can see over here in D, right? But here I can see this will shift here, this will shift here. Then 2-time resonance, where I can see 3-time resonance. So obviously that will make it, wait a minute, carbocatine stability by plus I n plus m in hyperconjugation. Let me see that. 2 times it is, and it is 3 times, right? Double bond will shift here, this will shift here, this will shift here. So extended conjugation in both of them, right? What is the reason they have given plus I and plus m in hyperconjugation? Plus m is also there. Hyperconjugation is also there in both the cases. Carbocation. Wait a minute. If I see this one, according to me, the answer should be D. Let me see the hyperconjugation here. If I see the hyperconjugation here, if this is shifting here, this is shifting here, right? Then you have a positive. Once it shifts, you have a positive here, and this is alpha, okay? Then hyperconjugation is there. If I see this one, if this bond is shifting here, this bond, wait a minute, let me see if positive, where you will have positive. If this bond is shifting here, this will have a double bond, and this will be, this bond is shifting here, here you will have a positive, and there is no resonance, okay. The resonating structures that you will draw here is, if this shifts here, this shifts here, this shifts here, the resonating structure will not have, yes, very good, huh? This question is quite a nice question. This will have a double bond, single bond, this is double bond, this is oxygen, and this will have a double bond, and this is O, because this bond has shifted here. So that is the reason this will be O positive, and this will be O negative here, na? Bond is shifting here. So no direct hyperconjugation you will see. Direct hyperconjugation you can't see here. This will be positive because that has shifted here. So no direct hyper, through this positive there is no, yes, right. So no hyperconjugation you can see. Here you can see hyper, no doubt its resonance, this resonance is better. But here you have 3 effects. This is hyperconjugation plus inductive plus mesomeric. Here you have mesomeric plus resonance. No doubt mesomeric is 3 times here. It is only 2 times here, but this is also extended. This is also extended. So B will be correct because of hyperconjugation here, right? Okay, that's a very good question. Huh? That's a very nice question. Even, because easily mistakes can be done here. So this is asked in JEE 2025. Then the next is the correct order of reactivity of electrophilic substitution. Now electrophilic substitution reactivity will be there which has maximum electron density. So this give you, this is a deactivating group, this is giving you minus I and plus M. This is giving you minus I and minus M. This is giving you plus I. So maximum donation, if I see, it is there in case C. In case of D, it is minimum, right? So definitely right. So we can say in case of B, because there is no minus effect here, there is only plus effect. Then it is C, right? B, C, then it is A, D, right? So answer will be, yes, B. This is deactivating now, and which is very dominating, minus I is dominating, yes. So these two are deactivating groups. deactivating groups, right? This one is no effect, this one is activating, so it will be B, A, C and D. Yes, BACD. BACD, that means B is the correct answer here. So what we are going to see is that what effects they are going to show you, and which is deactivating, which is activating. So this, even though it has plus M, but it is a deactivating group, right? So that you have to consider, that I already told you. Next is correct order of stability of carbon ion. So now in this case, again you can apply Barhi here. See, back bonding you can't see, aromaticity you can see 1, 2, 3, 4, but this is anti-aromatic in nature, right? So you can just write it here, this is anti-aromatic in nature. What about this one? This is non-aromatic in nature. This is also non-aromatic in nature. This is aromatic in nature. So you will say that D is maximum and A is minimum, right? So answer will be D is the correct answer. This is all you have to know, that aromatic makes the ring really highly stable and anti-aromatic makes the ring very unstable, right? The increasing order of stability of following free radicals. If you see the stability of following free radicals, same as that, more the resonance, more the hyperconjugation, more will be the stability. If you see this, in case of when you have C6H5 rings, right, they will make resonance, right? That is why they are going to be highly stable. Then C6H5 then you have CH3. This is going to show you plus I effect. This is also going to show you plus I effect. So answer will be B is the correct answer. Why? Because C6H5 phenyl ring is going to show you resonance. More phenyl rings, more resonance. CH3 is going to show you hyperconjugation. 3CH3 means 9 hyperconjugating structure, and here you have 6 hyperconjugating structures. So obviously that is going to be the answer, right? Okay. Now last two topics, acidic and basic strength. Let's talk about that, right? Yes. Now let's talk about the last two topics of today's class, guys. First is acidic strength. So if you see, I have written the order of acidic and basic strength. You can go and check this out. Mineral, then sulfonic, picric, squaric, then diphenol, dinitrophenol, carboxylic acid, carbonic acid, that is H2CO3. Then you have mononitrophenol, phenol, ammonium ion. Then you have methanol, water, ROH, alkyne, ammonia, alkene, alkane, H2. This is a very, very important acidic strength order. Okay, this is quite important, so you must remember this as it is, right? You must remember this as it is, right? Now this I told you that more, if you talk about a good acid, that depends upon the stability of carbon ion, and carbon ion will be more stable if you have a good electron withdrawing group, and even if there is some kind of hydrogen bonding, then also it will make the carbon ion very good stability will be there for the carbon ion, right? Then let's talk about the ortho effect in case of benzene. Now in case of benzoic acid, right? So let's say you have this thing. So in case of benzoic acid, always remember, if you have a bulky group here, this bulky group can be NO2, R, CHO. This group should not be HDT, OH, NH2, CN, because they are not that bulky. So if you have a good bulky group here, like these groups here, then in that case, the plane will twist. This and this group and this COH will not lie in the same plane. So what exactly will happen? This plane and this plane will be different. Okay? These plane will be different. Here the plane will, right? The plane will be different in this case. Wait a minute, right? The plane will be different here. Let's say it is in this plane. It will be in a different plane. The planes are different here. Because of the different plane, what exactly happens, right? So I'll tell you. Here it is CH3COH. This is like this, right? Now here if you see, Here you have this kind of situation. There is conjugation here as well, right? Then there is conjugation here as well. Double bond, and this can also shift here. So cross conjugation it is showing, right? If you have a group that is very small, right, then what is happening? Again cross conjugation is happening, right? But if you have a very bulky group, then this group, okay, let's say you have any group here, right? Now if you have any group, right, now let's talk about a group which is not bulky and that is on the same plane. If that group is on the same plane, then what will happen? There is some group like you have OH group that is on the same plane. Now see what will happen. Now this resonance will take place like this, and here this bond will, the resonance will take place like this. Okay. Can you see now it is converted to an extended conjugation? Earlier it was a cross conjugation. If you don't have any group, it is a cross conjugation. If you have a group that is in the same plane, it is an extended conjugation, making the carbocation very stable, making the carbon ion very stable. So if you see, if it loses H positive, it will give this kind of resonance here, and it will also show this kind of, which will push. That means this OH group here is making sure that this resonance take place, which is making the carbon ion very stable. If let's say you have a group that is in some other plane itself, then this resonance actually will create cross conjugation. How? Then because now in this case what will start happening, this bond will shift here, then this bond can also shift here, actually this can also take place, right? Oye hoye, why? Okay, this can also take place, that this bond is shifting here, this bond is shifting here. So one bond is going here, one bond is going here. So that means the group should not be out of plane. If it is out of plane, then it is giving rise to cross conjugation, right? That means cross conjugation means it is decreasing the stability of carbon ion. That means it is decreasing the acidity. So that's why we say directly what you have to learn. If you have a group that is making it out of plane, if you have a bulky group, then the acidic strength will decrease. Just this thing. Very important point, that is your ortho effect. Right? Okay. So these are the kind of things that you should know, right? So JEE Mains 2021 question is, which of the following is strongest acid? So strongest acid, how do we define? So we should know that after losing H positive, which is going to make a stable carbocation, which is going to make a stable carbon ion. So it will make this kind of situation. It will make this kind of situation. So I can directly see this one will make it aromatic. And aromaticity is definitely more stable than any other thing, right? So definitely we know from Barhi that after back bonding you have aromaticity. If a compound is aromatic, that is very stable. So answer is going to be D is the correct answer here. JEE 2025 question they have asked the compounds that produces CO2 with aqueous NaHCO3. Now what are the compounds that will produce CO2? The compounds that are very good acids. So indirectly they have asked the acidic nature. So acidic nature, you know, this is phenol, this is benzoic acid, this is picric acid, this is no conjugation is there, this is OCH3, okay, right. So if you see the compound that will produce with this solution R, choose the correct answer from the following options. So okay, so what are the compounds that make? So D will not be there, right? Picric acid will be there, benzoic acid will be there. This is giving the electrons. So if this is negative, you are giving the electrons here, you are making it quite unstable, right? So this will be there, this will be there, and this will be there. So A, B, D, there is no Option like ABD, ABC, sorry, ABC. I'm sorry, ABC. Chalo, I'll just see the options only. A, B and E. E is not going to show it because plus M effect will make it unstable. A and C only. If I have to choose from the option, then I'll have to eliminate phenol because phenol is acidic, but there is no option that is giving A, B, C. So I'll select AC only because I can clearly see there is no resonance here. So D will not be there only, that I'm sure. Right? So D option is not correct. A and B, then why not C? Because picric acid, so I have to include, that is very highly acidic. So this is also eliminated. So E they are calculating here. E is also plus M effect it is showing. It is not making the phenol stable. So I'll say this ACD, wait a minute, ACD. Arey yaar, what is this? Why wrong answer? D to not, it will not show, right? Because there is no as such resonance here, right? So will not see ACD, right? It will be A and C only. Because if you see D is, there is no resonance here. It should be something else, right? Resonance is resonance. Then how come this is making it stable, right? So this is quite stable. This is quite picric acid is quite stable. Phenol is also quite stable, but still I don't have any option when there is phenol. If I have to select between phenol and this simple ring with COH, I'll select phenol, right? So answer will be A and C only, right? Okay. Next is JEE 2024 question. Ma'am, why not D? That produce this with NaOH solution? Yes. Why not D? Because guys, if you see in the case of D, there is no resonance. I have to make the structure quite stable. So this is, this will give rise to this kind of situation. It will give you this conjugation, but what about other thing? Is there any resonance? Is this cyclopropyl ring helping in any case? Right? Okay. Okay. Right, everyone? But wait a minute. If you see this here, yes. Okay. Chalo. Next is JEE 2024 question, that is match list 1 with list 2. So now you have to match list 1. Achha, this so we have seen it already. We have done it already, guys. We have done it. Right? Okay. Then next one is the ascending order of acidity of OH group in the following compounds. So if you see, this is 2 electron withdrawing group, making it quite stable. So E will be maximum, then there will be B. So E maximum, then there is B. So this is ruled out. Okay? Either of them. Then after this, I have to select whether it's C, B or D, then I can get the answer. C, D or D. I think D should be there because it is common. Let's see. After this, you should have, because this is giving the electrons, that is making it unstable. Right? There is no effect, so it will be D. So it is ruled out. After this, you will have C because it is giving the electron, so it is plus M effect it is showing. This is minus M effect. This is also minus M effect. Minus M effect. So after this, you will have C, and last will be BuOH. That is no resonance where you have. So answer will be D is the correct answer here. Okay? Right? Chalo. Next is you have the ascending acidity of the following hydrogen atom. So you will see the ascending acidity of the following hydrogen atom. If you see, this will give you negative on sp hybridized. This is sp2, this is sp, this is sp3, this is also sp3. So more the sp, we know that electronegativity sp, then you have sp2, then you have sp3. So sp has maximum electronegativity, so maximum minus I effect will be there, right? So you can say here you will have negative charge on a carbon which is highly electronegative, that will make it very stable, right? So you should have A, B, then C. And out of this, if you lose hydrogen, you will have negative here and negative here. This is going to make it more unstable as compared to this one. So you should have A, B, D, C. A, B, D, C. A, B, D, C in the decreasing order. So answer will be, this one is the correct answer. Okay. So I'm just playing with sp2, sp3, hybridized orbitals. Let me see how many more questions. Chalo, let's see this one. Arrange the following decreasing in the order of acidic strength. So again, 2022 question, latest it is. Now again, what you have to see, just write down. Para position, it will show minus I and minus N. Meta position does not show mesomeric, so it will only show minus I. Meta position, no mesomeric, only minus I. This will show you minus I and plus M. So if you talk about acidity, in acidity we are looking for electron withdrawing groups. So which one is a better electron withdrawing? This one is a good. So this one will be A is maximum. So answer already you have. A is maximum. After this you have, because maximum withdrawing is an A, then you have, in case of B and C, both are showing minus I, but we know that minus I by this one is better. So then B, then C, then you have plus M here, so that's why it is last one. So A, B, C, D, answer will be A is the correct answer here, right? Okay, so that's how you show that. Now in case of basic strength, last part here, in case of basic strength, just directly check the availability of lone pair electrons. So more is the electron density, more will be the basicity. It is directly proportional to electron donating groups. And more is the basic strength, less will be the stability of its conjugate acid, right? And less will be the solvation effect. Right, so when you see this, now let's talk about the ortho effect. In case of ortho effect, in case of basicity, things are different. If you have ortho substituents on 1 degree amine, then it decreases the basicity, right? Wait a minute. Have I written decreases the acidic strength in the ortho effect of acidity? It should be increasing here, my bad. Okay, I think by mistake I have written, have I also said that it is decreasing? Please correct it, it is increasing, okay? In case of benzoic acid, if you have on bulky group on this position, it increases the acidity here, right? It increases the acidity because it will take this out of plane. So it increases the acidity and basicity will be decreased. If you have bulky group, basicity on the ortho effect, basicity is decreased. And if you talk about 2 and 3 degree amines, then basicity is increased in that case. Okay. So let's see this one here. Chalo. If you see this one, you have a group that is bulky, but this is 3 degree. So that is why, and this is 2 degree, right? So that is why what will happen, they will increase the basicity. So more is the degree, more will be the basicity, right? More will be the electron availability, right? Okay. And when you talk about a group that is attached to primary amines, that is annuline, in that case, why basicity decreases? Again, because it moves out of the plane, then this can easily accept H positive. That is why what will happen, it will be converted to annuline, right? And because of this bulky group, the steric hindrance will be there. See, NH2 and this group is not bulky. This will not create any repulsion. But once it accepts H positive, then the repulsions will be there. That's why it will not try to. That's why aniline will be like, I don't want to accept any H positive. If I accept H positive, then this group will move out of plane. I'll have to change the planarity. That is why this aniline will not be able to accept the H positive, and that's why its basicity will decrease, and that is why that is called as steric inhibition effect, right? Steric inhibition protonation. That is why basicity decreases in case of annulenes. Okay. Now let's see last question, like last 2-3 questions here. Increasing order of basicity for the following intermediates. The increasing order of basicity for the intermediates. So basicity you have to talk about here. This is JEE 2020 question where we are talking about the basicity. So tell me everyone. So if you see this, if you see this here, increasing order of basicity for the following intermediates. Now in this case, if you see electron availability, we'll talk about, right? So more is the electron availability, more will be the basicity of that particular compound, right? So if you see this here, the basicity is inversely proportional to the electronegativity, because basicity is directly proportional to electron donating groups and inversely to electron withdrawing groups, right? So here we'll talk about the electron withdrawing effect here. So if you see here, this is giving you sp3 hybridized, this is sp2 hybridized, this is sp hybridized, okay? And here the electronegativity is high for sp, then sp2, then sp3, right? And that is the reason, if you see this here, right, this is CH3, this is again sp3 only, this is also sp, okay? So in increasing order of basicity they are talking about of the intermediate, increasing order of basicity. So if you see sp, and because it is inversely proportional to electronegativity, sp and sp, this is third and fifth, right? So they will be least one. So third and fifth is the least one, not in this, not in this, not in this. So you get your answer. Then you will have sp2, this is only second. Then you have sp3, that is first and fourth, right? And that's how you have your answer. Okay, so it is based on like sp is more electronegative than sp2, then sp3, and based on electronegativity, how you will tell, because basicity is inversely proportional to electron withdrawing, it is inversely proportional to the basicity, right, to the electronegativity, and that's how you will tell this. Next is increasing order of pKb. So basicity, we know that Kb is inversely proportional to pKb. So if you see this here, again availability of electrons on nitrogen, you should be able to tell, right? So if you see this nitrogen is involved in delocalization, this nitrogen is involved, this nitrogen is also involved, this nitrogen is not involved in delocalization. Here this nitrogen is getting electrons from both sides. So here if you see this particular, here you have least, that means here you will have least basicity, this will have maximum pKb value. So answer is going to be, you have your answer, that is this is the correct answer, okay, right? Yes everyone, so that's how you're going to tell, that you just have to check the availability of electrons here, that's it, nothing more, right? Okay, tell me, is that clear how we did this question? We are just going to check the availability of electrons here. Here electrons are being donated. Here the electrons are always available, right? They are not being donated, so they are always available. Here electrons of this nitrogen are being donated, this nitrogen are being donated, this nitrogen is available here. This nitrogen has availability of electron here, right? So maximum availability is in C. right? So if you see maximum availability, that means Kb value of C is maximum. No, C is not maximum. Okay. Then you have B. Then you have availability is less here. So answer will be C, B, A. Yes. Okay. So that is your correct answer here, right? Yes. Tell me. Right, everybody? Right, everyone? So that's it for today, right? Do let me know how was the session, everyone, right? Okay. Do let me know, everyone, how was the session? Yes, students, tell me. Everything clear? Any problem you have? Any problem? Any problem? Tell me. Wait a minute. Wait a minute. C. Then you have, wait a minute. C is going to show the availability of lone pair, right? In this case, these lone pairs and these lone pairs are not available. These lone pairs are available. In this case, see guys, first thing is, see one thing. You have 2 nitrogens here. You have 3 nitrogens here. You have only 1 nitrogen here, right? Okay. Here it is fully available. This is not fully available, right? If you see this, let me just write down for Kb value. This is fully available in this case. This one is fully available, right? Wait a minute. This one is fully available in this case, right? In this case, this particular nitrogen is fully available here, right? This is fully available. And half of this is available. Here it is fully available. Half of this is available. Here this one is fully available and the electrons are being donated also, right? But here you have only 1 nitrogen which is fully available, right? So definitely B is then going to show you maximum. If you talk about the Kb value, B is going to show you the maximum Kb value. Because 2 nitrogens are half available, like electrons are delocalized, but still they are somewhat available. Full 1 nitrogen electron availability is there. Here also 1 full is available and this one is available. Then you will have A, then you will have C. So opposite will be B, A, and this is C. So BAC is this one only. So C will be the correct answer. Okay? Okay? Got it? Tell me. Okay, you should, it's not like only plus psi effect, ma'am. Here it is, ma'am, resonance is going. You have to see that these two are fully available. This is also fully available, but here extra 2 nitrogens are available. Extra 1 nitrogen is available. Okay, right? Tell me. Clear, everyone? Any problem? Any problem? Right? So that's it for today, guys. Now I'm very happy, right, that we are doing this here, right? And I'll love to see you, all of you, in the Sigma batch as well. Like, more things are happening there, so I don't want you to miss anything there, right? So yes, one more thing, guys. Tomorrow I have the lecture that is at 5 p.m. We are going to do electrochemistry, like really 3-hour session that is going to be same, right? So we'll see you all tomorrow at 5 p.m. for electrochemistry. Till then, bye-bye. Take care. See you all. Bye-bye, everyone. Bye-bye. And do let me know in the comment sections that how do you like this session? You want more of these sessions or not? Do let me know in the comment section. I want the comment section to be fully filled. If you enjoyed this, you have to write it. Otherwise, I'll feel that you have not enjoyed it. There is no point of writing it there. You have to write it in the comment section, because comment section stays. Can you see these comments? It stays, right? That's why write down in the comment section, so that I can also, whenever I feel, I don't want to teach today, I just go through your comments and I feel happy and like, yes, again motivated. So write it down in the comment section, right? Okay, thank you Aishwarya, Pranav, Are, thank you everyone. Chalo, okay then, bye bye, take care, see you all in the next class, bye bye.